Imagine attempting to toss a needle onto a spinning phonograph and observing it land flawlessly within the groove. You then follow the spiral for precisely a single turn before lifting it away into the darkness. The mathematical likelihood of this event near zero. Nevertheless, 3i Atlas has achieved exactly this with our whole solar system, threading the cosmic needle with retrograde exactitude and carrying out a grand tour that sidesteps perilous gravitational encounters while preserving ideal observational geometry. Within a cosmos ruled by chaos and chance, such precision seems almost deliberate. Prepare yourself as I delve into whether we are observing the universe's most unlikely accident or its most graceful design. Part 1. Was 3i Atlas's trajectory chosen? After 1i Oumuamua astonished us in 2017 and 2i Borisov came after in 2019, I believed I comprehended what these visitors might appear to be. I was mistaken. On July 1, 2025, telescopes in Chile spotted something remarkable. An object traveling at 57,000 kilometers per second, rapid enough to orbit Earth in fewer than 12 minutes, was nearing our Sun on what astronomers term a hyperbolic trajectory. In simple terms, this entity was not constrained by our star's gravity. It originated from another place, and it is returning to another place. Yet, this is where the narrative becomes compelling. This interstellar traveler, named 3i Atlas, was not simply tumbling through space on some arbitrary course. Instead, it seemed to glide along the plane of our solar system. This is the same unseen disk where Earth, Mars, Jupiter, and every planet orbits. But it was moving in the completely reverse direction, akin to a motorcyclist speeding backward on a freeway, holding perfect lane discipline as everyone else moves forward. The accuracy was disquieting. At an inclination of 175 degrees, 3i Atlas fell short of a perfect retrograde alignment with our planetary plane by a mere 5 degrees. In the boundless expanse of space, where objects can arrive from virtually any direction, what are the chances of such precise geometry? As astronomers charted its course, additional peculiarities came to light. The object was set to swing by Mars at just 1/5 of an astronomical unit, roughly 19 million miles, close enough for a brief wave, but not near enough for any substantial gravitational effect. It would then pass Venus at 0.6 of an AU. Following that, after circling the Sun at its nearest point on October 29th, it would pass Earth at 1.8 astronomical units, approximately 270 million kilometers away. Lastly, a more remote rendezvous with Jupiter was scheduled for March of 2026. It sounds like an itinerary, a grand tour of the inner solar system, meticulously arranged to steer clear of getting too near any individual world, yet situated to observe them all. However, perhaps most fascinatingly, 3i Atlas timed its arrival to align with what astronomers call solar conjunction. During its closest passage to our star, the object would be concealed behind the Sun from our viewpoint on Earth, rendering detailed observations almost unachievable. This seems like a convenient coincidence for something that supposedly lacks an agenda. Unlike Oumuamua, which left us pondering its strange acceleration and total absence of visible outgassing, 3i Atlas declared its presence with all the characteristics of a conventional comet. Images from the Hubble Space Telescope showed a radiant coma, that hazy envelope of gas and dust that materializes when ice sublimates in the solar wind. A faint tail was even present, precisely what one would anticipate from a piece of dirty ice visiting from the frigid depths between stars. Still, something seemed amiss. Initial observations indicated that most of the luminosity was focused ahead of the object's direction of movement, while that telltale tail remained stubbornly faint. Some researchers started to murmur about forward scattering effects and atypical dust dynamics. Others questioned if they were witnessing something novel, an artificial object crafted to resemble a natural comet. The speed itself conveys a narrative. At 57 to 58 kilometers per second relative to the Sun, 3I Atlas travels with a velocity characteristic of objects in our galaxy's stellar vicinity. It is not the blistering speed one might expect from something intentionally propelled across interstellar distances, but it is not suspiciously sluggish either. It possesses the Goldilocks of cosmic velocities, not too rapid, not too slow, but perfectly suited to blend in with the natural background hum of galactic motion. Size estimations fluctuated wildly during those initial weeks. Early accounts proposed a behemoth up to 20 kilometers wide, large enough to contain entire cities if it were hollow. But as Hubble's keen vision peered through the surrounding coma, a different reality took shape. The nucleus seemed to be far smaller, maybe only a few kilometers in diameter, potentially even less than a kilometer. While still significant, it was hardly the colossal mothership that early observations had suggested. The timing of 3I Atlas's arrival feels important in ways I am only starting to grasp. I live in an age when astronomical surveys are more sensitive than ever. Initiatives like the Asteroid Terrestrial Impact Last Alert System, or ATLAS, sweep the skies nightly, designed to detect potentially hazardous asteroids but perfectly situated to find interstellar interlopers. The Vera C. Rubin Observatory, soon to be operational, is projected to identify dozens of these visitors over the next decade. Are we simply becoming more adept at spotting what was always present? Or is something dispatching more visitors in our direction? The scientific community handles 3I Atlas with a caution born from difficult experience. Oumuamua taught us that these objects can defy our assumptions in ways that test our grasp of physics. Some mainstream astronomers believe 3I Atlas will turn out to be precisely what it seems: an interstellar comet adhering to the predictable laws of celestial mechanics, with any seeming irregularities explained by observational bias and the peculiarities of orbital dynamics. However, a vocal minority contends that more exotic possibilities should be considered. After all, if a sophisticated civilization wished to investigate our solar system, how might they proceed? Would they send an obvious artificial probe that announces alien technology to anyone with a telescope? Or would they engineer something that appears exactly like the kind of natural debris we would anticipate from interstellar space? This question lingers over our observations like a cosmic Rorschach test. Do I perceive patterns and intention because they genuinely exist, or because our pattern-seeking minds impose a narrative where only chaos prevails? When 3I Atlas vanishes behind the Sun during its closest approach, am I witnessing meticulously planned reconnaissance or merely the predictable geometry of orbital mechanics? Both NASA and the European Space Agency have released statements affirming that 3I Atlas presents no danger to Earth. The nearest it will approach is still over 4 times the distance to our Moon, a comforting safety buffer. Yet safety was never the primary concern. The concern is far more fundamental. Am I alone in the universe, or am I being observed? As 3I Atlas proceeds on its path toward perihelion, every observation yields new data and new inquiries. Spectroscopic analysis could uncover chemical fingerprints that differentiate between a natural comet and something more unusual. Thermal imaging might pick up heat signatures inconsistent with passive solar heating. Radio telescopes are listening for any signal, no matter how faint, that could hint at an artificial origin. The object will stay observable through September 2025 before the Sun's glare makes tracking impossible. Then, in early December, it will reappear from conjunction, possibly changed by its close encounter with our star. Comets often appear different after passing perihelion. They can be brighter, more active, and sometimes even break apart under thermal strain. What I observe in those December observations may finally resolve the question that has troubled us since that July discovery. Was 3I Atlas's trajectory chosen, or did I simply choose to notice it? In a universe where intention and coincidence can appear remarkably alike, the difference is more significant than I might wish to acknowledge. Part 2. The Discovery. Atlas spots an interstellar interloper. At times, the most remarkable discoveries start with the most conventional observations. On the evening of July 1, 2025, two robotic telescopes at the Atlas facility in Rio Hurtado, Chile, were performing their nightly routine, systematically sweeping the sky for any moving object. Their mission is ordinary yet vital, to find asteroids that could pose a threat to Earth before they find us. The computers flagged Object 11PAL3Z as unusual almost instantly. It was not because it seemed especially exotic, just a dim point of light drifting across the starfield like thousands of others. But this point was moving in the wrong direction, at the wrong speed, and with the wrong orbital parameters for anything originating in our solar system. Within 24 hours, the Minor Planet Center in Cambridge, Massachusetts, the official hub for small body discoveries, had verified what the automated systems suspected. This was not another common asteroid or comet. The object, designated 11P3Z, was moving on a hyperbolic trajectory with an eccentricity of approximately 6.1. In orbital mechanics, any object with an eccentricity exceeding 1 is unbound, which means it will never come back. This visitor was just passing by, not taking up residence. The formal declaration was made on July 2nd. Humanity had located its third confirmed interstellar object. The designations followed with bureaucratic exactness. 3I Atlas for the Interstellar Catalog and C 2025 NQN for the Comet designation, acknowledging the mounting evidence of outgassing activity that set it apart from its mysterious predecessor, Oumuamua. But the discovery timeline was not so straightforward. As is common in astronomy, the discovery was in fact a rediscovery. Archival searches showed that both Atlas telescopes and the Zwicky Transient Facility had taken images of the object as early as June 14th, and possibly even before. These recovery observations are invaluable to asteroid hunters. They push the observational arc back in time, significantly enhancing orbital calculations and forecasts. The figures were astounding. At the time of discovery, 3I Atlas was already 4.5 astronomical units from the Sun, about the distance of Jupiter's orbit, and was traveling at 61 kilometers per second. That translates to 137,000 miles per hour, fast enough to traverse the United States in under 2 minutes. Even more impressively, when astronomers determined its velocity relative to the Sun after factoring in our star's gravitational pull, they found it was moving at 57 to 58 kilometers per second. This is precisely the kind of speed one would expect from an object that originated in interstellar space and was drawn into our solar system's gravitational well. The global astronomical community reacted with the type of coordinated efficiency that makes one appreciate living in the 21st century. Within hours of the Minor Planet Center's circular announcing the discovery, observatories on 6 continents were directing their instruments toward the coordinates. Amateur astronomers collaborated with professional teams in a worldwide effort to monitor the object's brightness, position, and any signs of activity. The Virtual Telescope project in Italy quickly organized public viewing events, broadcasting live images as 3I Atlas moved across the background stars. Radio telescopes started to listen for any signals. Space agencies issued the first of many press releases, carefully striking a balance between excitement and scientific prudence. NASA's communication was especially deliberate, highlighting 3 key points. Yes, this was truly interstellar. No, it presented no threat to Earth. And yes, it offered an unparalleled chance to examine material from another star system. The European Space Agency reiterated these sentiments, mentioning that their future Comet interceptor mission, designed to rendezvous with a pristine comet from the outer solar system, could act as a model for future encounters with interstellar visitors. Early size estimates turned out to be wildly variable, spanning from a few hundred meters to several kilometers in diameter. The difficulty is in distinguishing between the nucleus itself and the surrounding coma of gas and dust. Without knowing the object's albedo, how much sunlight it reflects versus absorbs, and without understanding the contribution of outgassing to its total brightness, astronomers were essentially making educated guesses. This uncertainty resulted in some rather sensational early headlines. Several news outlets reported a potentially enormous object up to 20 kilometers wide hurtling through our solar system. The reality, as observations from the Hubble Space Telescope would later show, was more modest but just as captivating. The confusion arises from a basic challenge in observing asteroids and comets. When you view these objects through a telescope, you are not seeing the solid surface as you would with Mars or Jupiter. Instead, you are seeing scattered sunlight from both the nucleus and any surrounding dust or gas. Differentiating these contributions necessitates sophisticated modeling and numerous observations at various wavelengths and phase angles. For 3I Atlas, this issue was worsened by its clear activity. Unlike Oumuamua, which exhibited no visible signs of outgassing, this new visitor displayed a distinct coma from the moment it was found. That hazy envelope of sublimated ice and released dust makes precise size measurements nearly impossible without thorough analysis. The media attention was instantaneous and fierce. CNN aired segments comparing 3I Atlas to Oumuamua and speculating about its origins. The Guardian published articles explaining interstellar objects and what their compositions might reveal about other planetary systems. Science journalists worked tirelessly to translate orbital mechanics into understandable language for curious readers. But perhaps more revealing was what the discovery showed about our own abilities. The detection of 3I Atlas proved just how much our astronomical infrastructure had advanced since Oumuamua's surprise arrival 8 years prior. We now have better surveys, faster follow-up networks, and more sophisticated analysis tools. We were no longer completely unprepared for interstellar visitors. The Atlas system itself merits special recognition. Funded primarily to locate potentially hazardous asteroids, its 4 telescopes, 2 in Hawaii, 1 in Chile, and 1 in South Africa, act as a sort of early warning system for threats from space. That this network also serves as humanity's primary line of detection for objects from other star systems is a fortunate accident of geometry and timing. As July progressed into August, the observation campaign grew more intense. Ground-based telescopes monitored 3I Atlas's brightness and color, searching for indications of how its activity might change as it neared the Sun. Space-based instruments like Hubble readied for detailed imaging sessions that would unveil the object's true nature. The discovery had settled one vital question. We were indeed observing humanity's 3rd confirmed interstellar visitor, but it had brought forth dozens more. Where exactly had this object come from? What was its internal composition? How large was its nucleus beneath that expanding coma? And perhaps most fascinatingly, why did its trajectory seem to follow such a precise path through our planetary system? Amateur astronomers and professional researchers alike braced for the months to come, knowing that 3I Atlas would grow brighter as it approached the Sun, potentially unlocking secrets about the formation and evolution of planetary systems light years away from our own. The discovery phase had concluded. Now came the far more demanding task of understanding what we had found. The night sky had presented another puzzle, encased in the deceptive simplicity of a moving point of light. As telescopes across the world continued their patient observation, one thing was clear. 3I Atlas was poised to teach us something new about the universe we thought we understood. Part 3. A rare visitor, only the 3rd of its kind. Suppose meteorites were as infrequent as winning lottery tickets. You might live your entire life without ever hearing of a single confirmed instance, let alone seeing one for yourself. This is effectively the situation we were in with interstellar objects until quite recently. Throughout all of human history, we had never consciously observed a single visitor from another star system journeying through our cosmic vicinity. Then, in October 2017, everything was altered with Oumuamua. The name translates to scout or messenger in Hawaiian, and it certainly fulfilled its role as a harbinger of things we did not anticipate. Oumuamua came with credentials that loudly proclaimed it was not from this area: a hyperbolic orbit, a reddish hue, and an elongated form unlike anything in our solar system's collection of asteroids and comets. But what truly seized scientific interest was not what it was, but what it did. As Oumuamua circled the Sun and started its return journey to interstellar space, astronomers noticed something unprecedented. The object was speeding up, not drastically, but measurably, in a manner that could not be accounted for by gravitational forces alone. The acceleration was slight, about 17 meters per second integrated over its entire solar passage, but it was real and directed away from the Sun. This non-gravitational acceleration ignited a scientific debate that persists to this day. The conventional explanation centers on outgassing, the concept that as Oumuamua warmed near the Sun, subsurface ice sublimated and formed tiny jets that propelled the object forward. The problem was, no one could observe any proof of this outgassing. There was no coma, no tail, and no spectroscopic signs of water or other volatiles. It was like watching a car accelerate without hearing the engine. More unconventional explanations arose. Perhaps Oumuamua was composed mainly of hydrogen ice, which would sublimate without being seen. Or maybe it was actually a thin, flat object being pushed by solar radiation pressure, like a natural light sail. This latter theory, advocated by Harvard's Avi Loeb, raised the possibility that Oumuamua might be artificial, humanity's first encounter with technology from another civilization. 2 years later, Tuai Borisov appeared and acted as a sort of palate cleanser. Here was an interstellar object that behaved precisely as textbook comets are supposed to. It formed a stunning coma and tail as it approached the Sun. Spectroscopic analysis showed familiar signs of water vapor, carbon monoxide, and other volatile compounds. It even broke apart near perihelion, a common destiny for comets under thermal stress. But Tuai Borisov had its own surprises. Chemical analysis indicated it was unusually rich in carbon monoxide compared to comets from our own outer solar system. This was not necessarily strange. CO can be more prevalent in very cold regions, but it hinted that wherever Borisov came from, the conditions were different from the frigid domain where our own Oort cloud comets were formed. Now, 3I Atlas serves as a third data point in our developing understanding of interstellar visitors. Like Borisov, it displays clear indications of cometary activity, the comforting glow of a coma and the faint streak of a dust tail. But like Oumuamua, it poses questions that challenge our assumptions about what is normal for objects from other star systems. The scarcity of these detections until recently was not necessarily because interstellar objects were uncommon. Current estimates propose that at any given time there could be thousands or even tens of thousands of interstellar objects passing through our solar system. The issue was that they are typically small, dark, fast-moving, and very distant, exactly the type of targets that traditional asteroid surveys were ill-equipped to find. The situation changed with the creation of automated wide-field sky surveys designed primarily to locate potentially hazardous asteroids. Projects like Linear, Neowise, Atlas, and the Catalina Sky Survey were not specifically searching for interstellar visitors, but their sophisticated detection algorithms and quick follow-up capabilities made such discoveries almost certain. The Vera C. Rubin Observatory, currently being built in Chile, is set to revolutionize this field. With its 8.4-meter primary mirror and 3.2 gigapixel camera, Rubin will scan the entire visible sky every few nights, potentially finding 6 to 50 interstellar objects per year, depending on their size, distribution, and activity levels. What appears rare today may become common within a decade. This statistical reality provides an important perspective on claims that 3I Atlas is somehow special or targeted. When you increase your detection rate by orders of magnitude, you are bound to find objects with unusual traits simply due to larger sample sizes. Some will have orbital geometries that seem carefully arranged. Others might show unexpected spectroscopic signatures or brightness changes. The challenge is to differentiate between unusual because it is interesting and unusual because it is artificial. The public's fascination with these discoveries generates its own feedback loops. Media coverage of interstellar objects often concentrates on their mysterious or anomalous features, frequently at the cost of more ordinary explanations. This is not necessarily a bad thing. Wonder and curiosity fuel scientific investigation, but it can lead to hasty conclusions about the importance of specific observations. Social media magnifies these effects. A paper suggesting that an interstellar object's trajectory shows signs of artificial guidance can become viral before peer review has had a chance to spot methodological errors or alternative interpretations. The speed of information spread often exceeds the deliberate pace of scientific verification. Yet there is immense scientific value in every interstellar visitor, whether it turns out to be natural or artificial. Each object contains information about the stellar system, where it originated, chemical signatures, isotope ratios, structural characteristics that cannot be obtained in any other way. They are like geological samples from worlds we will never visit, delivered to our doorstep free of charge. For 3I Atlas specifically, the combination of visible activity and accessible geometry makes it especially valuable. Unlike Oumuamua, which was discovered when it was already on its way out and could only be observed for a few weeks, 3I Atlas was detected months before its closest solar approach. This extended observation period allows for detailed spectroscopic campaigns, thermal modeling, and precise astrometry that can reveal subtle details about its composition and structure. The object also serves as a test case for our institutional responses to unusual discoveries. How quickly can the global astronomical community coordinate observations? How effectively can we convey uncertainty to the public without either dismissing intriguing possibilities or promoting baseless speculation? What occurs when tentative scientific hypotheses clash with our cultural narratives about contact with extraterrestrial intelligence? These lessons are important because 3I Atlas will not be our last interstellar visitor. The Rubin era will bring us dozens more, each potentially possessing its own unique traits and challenging our understanding in different ways. Some may be completely ordinary chunks of ice and rock. Others might display properties that push the limits of what we consider natural. The rarity of interstellar objects is already becoming a thing of the past. What remains rare is our experience in studying them systematically, and our wisdom in interpreting what we find. 3I Atlas represents not just our third confirmed interstellar visitor, but our third chance to practice the delicate art of scientific investigation under intense public scrutiny. As we prepare for a future where such discoveries become common rather than extraordinary, the lessons we learn from 3I Atlas may prove as valuable as any specific scientific data it provides about its own nature and origin. Part 4. The Trajectory Puzzle, Geometry, Speed, and Flybys. Envision a cosmic billiard table where someone has just made the most improbable shot in history. The cue ball, our 3I Atlas, approaches from the darkness beyond the table's edge, moving at precisely the right angle and speed to glide along the felt surface, gently pass several other balls with mathematical exactitude, then roll off the opposite side and vanish into the void. The precision is so extraordinary that you find yourself asking, was this shot intentional? In terms of orbital mechanics, 3I Atlas is on what astronomers describe as an extremely hyperbolic trajectory with an eccentricity of approximately 6.1. To grasp what this signifies, consider the difference between a circle, an ellipse, and a hyperbola. Planets move in ellipses with eccentricities less than 1. Earth's orbit has an eccentricity of just 0.017, making it nearly circular. A perfect circle has an eccentricity of exactly 0, while a parabola, the mathematical line between bound and unbound motion, has an eccentricity of exactly 1. Anything with an eccentricity greater than 1 follows a hyperbolic path, meaning it is traveling too fast for the Sun's gravity to capture it for good. 3. Atlas, with its eccentricity of 6.1, is so unbound that it will leave our solar system moving almost as fast as it arrived, having borrowed only a small amount from the Sun's gravitational well. But it is the geometry of this hyperbola that is causing a stir. The object is approaching our solar system from the general direction of Sagittarius toward the center of our galaxy, which might sound significant until you realize that this is actually a fairly common direction for interstellar objects, given our galaxy's rotation and stellar dynamics. There is nothing particularly special about that trajectory except for one detail. 3I Atlas maintains an inclination of approximately 175 degrees relative to the ecliptic plane, that unseen disk where all the planets orbit. This means it is traveling in a retrograde direction opposite to the motion of the planets. But here is the critical part. It is only 5 degrees away from perfect alignment with that plane. Think about this in 3 dimensions. An object can approach from literally any direction, up, down, sideways, at any imaginable angle. The ecliptic plane makes up a tiny fraction of all possible orientations, yet 3I Atlas hits it almost perfectly. It is like throwing a frisbee into a parking garage and having it somehow end up sliding along the floor instead of hitting the ceiling, walls, or any of the countless other available surfaces. The sequence of planetary encounters adds another dimension to this geometric puzzle. On October 3, 2025, 3I Atlas will pass within 0.19 astronomical units of Mars, about 19 million miles, which sounds distant but is a relatively close encounter in solar system terms. On November 3, it will sweep past Venus at 0.65 astronomical units. Then, after circling the Sun at its closest approach on October 29th at approximately 1.36 to 1.4 astronomical units, just inside Mars's average orbital distance, it will continue outward for an Earth flyby on December 19th at 1.8 astronomical units. Finally, on March 16th, 2026, it will encounter Jupiter at 0.36 astronomical units, about 34 million miles from the giant planet. Each of these distances is large enough to prevent any significant gravitational interaction. 3I Atlas is not using these planets for gravity assists in the way interplanetary spacecraft do. It is not borrowing orbital energy to alter its trajectory. The encounters are more like cosmic near misses, close enough to be noteworthy, far enough to be safe, and precisely spaced to create what almost looks like a planned schedule. The speeds involved are equally remarkable. At discovery, 3I Atlas was moving at approximately 61 kilometers per second relative to the Sun. As it nears perihelion, gravitational acceleration will increase this to nearly 68 kilometers per second. But perhaps most importantly, its velocity relative to the local galactic neighborhood, what astronomers call V-infinity, is 57 to 58 kilometers per second. This is not the blistering speed you might expect from an artificial probe launched between star systems. It is exactly the kind of velocity you would predict for debris that originated in another stellar system and was captured by our Sun's gravitational influence. Being too fast to be natural would actually seem suspicious. Being too slow would also be strange. 3I Atlas moves at the perfect Goldilocks velocity, not too fast, not too slow, but just right to blend in with the natural background of interstellar material. Yet there is something unsettling about the timing. As 3I Atlas approaches its closest point to the Sun, it will pass through what astronomers call solar conjunction. The object will be positioned behind the Sun as seen from Earth, making detailed observations nearly impossible during its most active phase. This is not unusual for objects with perihelia around 1 to 2 astronomical units, but it certainly complicates things for scientists trying to study the visitor during its most interesting period. The Hubble Space Telescope has created spectacular trajectory visualizations showing 3I Atlas's path as a graceful hyperbola weaving through the solar system. These diagrams reveal the ballistic precision of celestial mechanics, how gravity shapes motion across millions of miles with mathematical perfection. But they also highlight the apparent intentionality of the path, the way it seems designed to offer glimpses of multiple worlds without getting close enough to any of them to be captured or deflected. Observational uncertainties add another dimension to the puzzle. While the general shape of the trajectory is well known, precise distances and timing still have error margins. The quoted perihelion distance of 1.36 to 1.4 astronomical units reflects current uncertainties in the orbital solution. Similarly, the various planetary encounter distances are predictions based on current trajectory calculations, not predetermined destinations. This uncertainty is both frustrating and important. It is frustrating because it prevents us from making definitive statements about the object's path. It is important because it reminds us that what appears to be precision in celestial mechanics can actually reflect the limitations of our observational capabilities rather than true cosmic choreography. Additional astrometric observations continue to refine these orbital elements. Each new position measurement helps to shrink the error ellipses around predicted future positions. By the time 3I Atlas reaches perihelion, we will have a much more precise understanding of exactly where it is going and when it will get there. The trajectory raises fundamental questions about the nature of coincidence in the universe. How often do random journeys through interstellar space produce paths that look this organized? Is apparent design an inevitable result of improved detection capabilities? We notice the unusual cases precisely because they are unusual, or does it reflect something more intentional? As 3I Atlas continues its precisely choreographed dance through our solar system, these questions become more than academic curiosities. They challenge our understanding of what constitutes evidence for intelligence in a universe where natural processes can produce patterns that look remarkably purposeful. The geometry is clear, the interpretation remains tantalizingly ambiguous. Part 5. Comparing to Oumuamua, a different flavor of weird. If interstellar objects were individuals appearing at your door unannounced, Oumuamua would be the enigmatic stranger in a trench coat who leaves no fingerprints, while 3I Atlas would be the talkative neighbor who seems perfectly ordinary until you realize they know a bit too much about your daily schedule. Both are unsettling, but in entirely different ways. Oumuamua entered our consciousness in October 2017 as humanity's first confirmed interstellar visitor and immediately broke every rule we thought we understood about how such objects should act. The strangeness started with its shape. Spectacularly elongated, perhaps 10 times longer than it was wide, tumbling end over end, like a cosmic cigar or needle. Nothing in our solar system resembles Oumuamua, which instantly raised questions about how such an object could form naturally. But the real puzzle was its motion. As Oumuamua rounded the Sun and began its journey back to interstellar space, precise tracking revealed something unprecedented. The object was accelerating away from the Sun in a way that could not be explained by gravity alone. The acceleration was small, about 17 meters per second total, but it was measurable, consistent, and completely unexpected. For comets, such non-gravitational acceleration is common. As these dirty snowballs approach the Sun, subsurface ice begins to sublimate, creating jets of gas that push the comet around like tiny rocket engines. But Oumuamua showed no visible signs of this outgassing activity. No coma, no tail, no spectroscopic signatures of water vapor or other volatiles. It was accelerating like a comet while looking like an asteroid. The scientific community responded with creative explanations. Perhaps Oumuamua was composed primarily of hydrogen ice, a form of frozen hydrogen that would sublimate invisibly, leaving no detectable signature in our telescopes. Maybe it was covered with an organic coating that prevented us from seeing the underlying ice. Or possibly it was venting material from its sides rather than creating the sunward-pointing jets typical of active comets. The most exotic hypothesis came from Harvard's Avi Loeb, who suggested that Oumuamua might actually be artificial, a light sail pushed by solar radiation pressure rather than outgassing. This would require the object to be extremely thin and flat, more like a cosmic pancake than the elongated needle suggested by its brightness variations. Loeb argued that while this interpretation might seem far-fetched, it actually fit the observations better than any of the proposed natural explanations. Tuai Borisov, discovered in August 2019, served as a kind of cosmic palate cleanser after Oumuamua's enigmas. Here was an interstellar object that behaved exactly as astronomy textbooks said comets should behave. As it approached the Sun, it developed a spectacular coma and tail. Spectroscopic analysis revealed familiar signatures of water vapor, carbon monoxide, and cyanide, the standard suite of volatiles expected from sublimating ice. Borisov even fragmented as it rounded the Sun, breaking apart under thermal stress in a display that would have looked perfectly normal if it had been a comet from our own Oort cloud. The only unusual characteristic was its chemistry, particularly high concentrations of carbon monoxide compared to typical solar system comets. But this difference was easily explained by formation in a colder environment around a different star. Now, 3I Atlas presents us with a third model of interstellar behavior, combining elements from both predecessors while introducing new puzzles of its own. Like Borisov, it shows clear signs of cometary activity from the moment of discovery. Hubble Space Telescope images reveal a well-developed coma and a faint anti-solar tail, exactly what you would expect from sublimating ice-releasing dust into space. But the activity pattern is subtly different. Early observations showed most of the object's brightness concentrated in a sunward direction ahead of its motion, with the traditional anti-solar tail remaining relatively weak. This forward-scattering brightness pattern is not impossible for a natural comet, but it is unusual enough to raise questions about the dust's properties and distribution. Size constraints tell another interesting story. Initial reports suggested 3I Atlas might be enormous, potentially up to 20 kilometers in diameter. But as Hubble's sharp vision cut through the surrounding coma, a different picture emerged. The nucleus appears to be much smaller, with current estimates suggesting a radius of less than 2.8 kilometers, possibly as small as a few hundred meters. This size revision matters because it affects calculations of dust production rates and outgassing efficiency. A smaller nucleus would need to be much more active per unit surface area to produce the observed coma, potentially indicating either unusual composition or structural properties that distinguish it from typical solar system comets. The dust mass loss rate estimates range from 10 to 120 kilograms per second, depending on assumptions about grain size distribution and density. These numbers sound impressive until you realize that even the high end represents a tiny fraction of the object's total mass. A few kilometer nucleus could sustain such losses for thousands of years without significantly depleting its volatile reserves. Morphological analysis of the Hubble images reveals another intriguing detail. The sunward dust emission appears to originate from the day side of the nucleus, consistent with solar heating driving sublimation. This is exactly what you would expect from a natural comet. Yet the geometry creates an appearance that some observers have interpreted as unusual or potentially artificial. The spectroscopic story continues to evolve as 3I Atlas approaches the Sun and signal-to-noise ratios improve. Early attempts to detect gas signatures have yielded ambiguous results, not surprising given the object's distance and the inherent challenges of observing faint emission lines against the background sky. The experience with 2I Borisov reminds us that patience is essential. Many of that object's most interesting chemical signatures only became apparent during its closest solar approach. What emerges from this comparison is a pattern of increasing familiarity combined with persistent anomalies. Oumuamua was thoroughly alien. Nothing like it existed in our catalogs of solar system objects. Borisov was reassuringly familiar, despite its interstellar origin. 3I Atlas occupies a middle ground, obviously cometary, yet subtly different in ways that keep nagging at the edges of our understanding. The brightness evolution provides another point of comparison. Oumuamua's light curve showed dramatic variations consistent with a highly elongated, tumbling object. Borisov's brightness increased predictably as it approached the Sun, following the standard relationship expected for sublimating ice. 3I Atlas displays brightness patterns that are mostly consistent with cometary models, but with subtle deviations that have sparked debates about dust-scattering properties and potentially unusual nucleus characteristics. Perhaps most importantly, the sequence of these three discoveries illustrates how our understanding of interstellar objects continues to evolve. Each visitor teaches us something new about the possible range of properties and behaviors we might expect from debris originating in other stellar systems. Oumuamua expanded our conception of what was possible. Borisov reassured us that familiar physics still applies. 3I Atlas suggests that the truth might lie somewhere in between, objects that are recognizably natural yet distinctly foreign. The observational challenges also differ significantly. Oumuamua was discovered when it was already outbound, providing only a few weeks of useful observations before it faded beyond detection limits. Borisov offered a more generous timeline, remaining observable for nearly a year as it made its closest approach to the Sun. 3I Atlas provides perhaps the best observational opportunity yet, discovered months before perihelion and positioned for extended monitoring through multiple phases of its solar encounter. This extended observation window allows for more sophisticated analysis techniques. While Oumuamua's mysterious acceleration had to be inferred from precise astrometry over a short time baseline, 3I Atlas can be monitored for any signs of non-gravitational forces over many months. If the object were to display unexpected trajectory deviations, we would have much better data to distinguish between natural outgassing effects and more exotic possibilities. The public and scientific reception of these discoveries also reveals interesting patterns. Oumuamua generated intense debate precisely because it defied easy categorization. Borisov was largely welcomed as a return to normalcy, an interstellar object that behaved as theory predicted. 3I Atlas rekindles the controversy, not because it is as dramatically anomalous as Oumuamua, but because its subtle unusualities leave room for multiple interpretations. The lesson from this trilogy of visitors may be that interstellar objects resist simple categorization. Each carries its own combination of familiar and foreign characteristics, reflecting the diverse conditions in the stellar systems where they formed. What looked like anomalies in Oumuamua might represent normal variations within a population we are only beginning to sample. Yet the nagging questions persist. If these objects are simply natural debris from other planetary systems, why do they keep surprising us? And if there is something more intentional, why do they work so hard to mimic natural phenomena? 3I Atlas, with its combination of obvious activity and subtle anomalies, seems designed to keep us guessing, though whether by cosmic coincidence or deliberate intent remains tantalizingly unclear. Part 6. Signs of Anomalies. What looks off and what doesn't? There is a point in every compelling mystery when you understand that the evidence is indicating two separate directions simultaneously. The butler possessed the means, motive, and opportunity, but so did the victim's business associate, and both of their alibis seem solid. This is essentially the situation I am in with 3i Atlas, gathering a set of observations that could bolster either a completely natural explanation or something significantly more fascinating. Let's begin with the most visually compelling anomaly, that nearly perfect alignment with our solar system's planetary plane. With an inclination of 175 degrees, 3i Atlas is on a retrograde path but remains within 5 degrees of the ecliptic. To the human eye, which is accustomed to thinking in terms of purpose and design, this appears almost deliberately arranged. Why would a random piece of debris from interstellar space happen to arrive along the exact plane where all our planets orbit? The astronomical explanation is more intricate than it initially seems. Survey selection effects have a crucial part to play here. Most asteroid and comet detection programs focus their searches near the ecliptic, where the overwhelming majority of solar system objects are found. We are much more likely to find objects that pass through these well-observed regions than those that approach from high inclinations where fewer telescopes are looking. Furthermore, the ecliptic is not just an arbitrary reference plane. It represents the gravitational midplane of our solar system, where the combined mass of the Sun and planets creates a kind of cosmic watershed. Objects coming from interstellar space undergo subtle gravitational focusing effects that can preferentially guide them toward this plane. So, while the alignment appears suspicious, it might actually be a natural outcome of solar system dynamics. The sequence of planetary encounters adds another layer of seeming intentionality. 3i Atlas will pass Mars at 0.19 astronomical units, Venus at 0.65 astronomical units, Earth at 1.8 astronomical units, and Jupiter at 0.36 astronomical units. When laid out in chronological order, this resembles a carefully planned grand tour of the inner solar system. But orbital mechanics presents a different perspective. These are not close encounters in any meaningful gravitational sense. The object will not experience significant deflection or energy transfer from any of these planets. The missed distances are large enough that 3i Atlas essentially disregards the planet's gravitational wells, continuing on its predetermined hyperbolic path with only minimal perturbation. More concerning to some observers is the timing of the solar conjunction. As 3i Atlas reaches its closest point to the Sun on October 29th to 30th, it will be positioned almost directly behind our star as seen from Earth. This makes detailed observations nearly impossible during what should be the object's most active phase, when heating effects are at their peak and any unusual characteristics might be most visible. Skeptics might argue that this timing seems convenient for something attempting to evade scrutiny. However, astronomers point out that solar conjunction is an unavoidable consequence of orbital geometry for any object with a perihelion distance of around 1 to 2 astronomical units. It is not hiding, it is simply following the predictable laws of celestial mechanics. The brightness morphology presents more subtle challenges to a straightforward interpretation. Hubble's Space Telescope images show most of the object's luminosity concentrated sunward ahead of its direction of motion, with a relatively weak traditional comet tail pointing away from the Sun. This forward scattering pattern is not impossible for natural dust, but it is unusual enough to spark debate. Some commentators have suggested that this brightness distribution indicates self-luminosity, the object generating its own light rather than merely reflecting and scattering sunlight. This would indeed be extraordinary, potentially pointing to internal energy sources inconsistent with passive rock and ice. But the Hubble analysis team interprets the same observations as normal illumination geometry combined with forward scattering dust properties. Size estimates have also generated confusion and speculation. Early media reports suggested a massive object, potentially 20 kilometers in diameter, large enough to house cities if it were artificial. These estimates were based on brightness observations that did not account for coma contamination and made conservative assumptions about surface reflectivity. As Hubble's sharp resolution began to separate the nucleus from its surrounding gas and dust envelope, a more modest picture emerged. Current models constrain the nucleus radius to less than 2.8 kilometers, with some solutions suggesting an object just a few hundred meters across. It is still substantial, but hardly the massive mothership that initial reports implied. This size revision actually creates new puzzles. A smaller nucleus would need to be remarkably active per unit surface area to produce the observed coma brightness. Either 3I Atlas is composed of unusually volatile material, or its internal structure allows for more efficient outgassing than typical solar system comets. The dust production rates estimated from Hubble observations range from 10 to 120 kilograms per second, depending on assumptions about particle size distribution. While these numbers sound impressive, they represent only a tiny fraction of the object's probable mass. Even a modest few-kilometer nucleus could sustain such losses for millennia without significant depletion. Chemical analysis remains frustratingly incomplete due to the object's distance and the current limitations of spectroscopic observations. Early attempts to detect specific gas species, water vapor, carbon monoxide, carbon dioxide, cyanide, have yielded ambiguous results. This absence of clear spectroscopic signatures does not prove the object is unusual. It might simply reflect the challenges of observing faint emission lines against the background sky. The experience with Tui-Borisov counsels patience here. Many of that object's most interesting chemical characteristics only became apparent as it approached perihelion, and warming effects boosted gas production to detectable levels. 3I Atlas may yet reveal distinctive compositional fingerprints as it draws closer to the Sun. Perhaps most intriguingly, some researchers have noted subtle asymmetries in the object's brightness and morphology that resist easy explanation through standard comet models. The sunward dust emission appears slightly offset from the nucleus center, potentially indicating localized outgassing from specific surface regions, rather than the more uniform activity typical of solar system comets. These morphological details matter because they could distinguish between thermal heating effects, which should create relatively symmetric outgassing patterns, and more exotic energy sources that might produce structured or directional emissions. However, interpreting such subtle features requires extremely careful calibration of instrumental effects and atmospheric distortions. The rotation state of 3I Atlas remains largely unknown, another gap that limits our ability to model its activity patterns. Most comets show clear periodic variations in brightness and morphology as different regions of their surfaces rotate into and out of sunlight. The absence of obvious rotational signatures could indicate either a very long rotation period, a nearly spherical shape, or a viewing geometry that minimizes the visibility of rotational effects. What emerges from this catalog of anomalies is a picture of an object that consistently challenges straightforward interpretation while remaining just within the bounds of natural explanation. Each unusual characteristic has potential conventional explanations. Yet the accumulation of subtle oddities creates a pattern that keeps nagging at the edges of scientific confidence. The crucial question becomes whether these apparent anomalies represent genuine departures from expected behavior or simply the inevitable result of studying an unfamiliar type of object with limited observational capabilities. Natural phenomena can look artificial when viewed through the lens of incomplete data, and human pattern recognition systems evolved to detect agency in ambiguous situations. As 3I Atlas continues its approach toward perihelion, each new observation carries the potential to either resolve these puzzles through conventional comet physics or deepen the mystery by revealing characteristics that push beyond the boundaries of natural explanation. The anomalies are real. Their interpretation remains tantalizingly open to debate. Part 7. Natural Explanations, the Comet Playbook. Sometimes the most graceful explanation is the most straightforward one, and in astronomy, that typically involves relying on the well-established physics of ice, dust, and sunlight. Despite all its unusual traits, 3I Atlas exhibits the fundamental characteristic that immediately classifies it as a natural object. It is actively outgassing just as a comet should. The basic physics are simple and have been refined over decades of studying comets throughout our solar system. As 3I Atlas nears the Sun, solar radiation warms its surface, causing subsurface ice to sublimate directly from solid to gas. This escaping vapor carries with it tiny dust particles that were mixed with the ice, creating the distinctive coma, that fuzzy envelope of gas and dust that surrounds the nucleus and makes it visible from vast distances. Hubble Space Telescope observations confirm that this process is happening exactly as theory predicts. The images show a well-developed coma with clear evidence of sunward dust emission and a faint anti-solar tail. The sunward emission occurs because that is where solar heating is most intense, driving the most vigorous sublimation. The tail forms as radiation pressure from sunlight pushes the lighter dust particles away from the nucleus, creating the classic comet appearance that has captivated humans for millennia. The dust production rates estimated from these observations 10 to 120 kilograms per second, depending on particle size assumptions, fall well within the range observed for active comets in our own solar system. While this might sound like a lot of material, it represents an infinitesimal fraction of the object's total mass. A nucleus just 2 kilometers in radius contains roughly 4 billion kilograms of material, meaning 3I Atlas could sustain current activity levels for thousands of years without noticeable depletion. Surface brightness modeling using Hubble data constrains the nucleus size to a radius of less than 2.8 kilometers, with some solutions suggesting an object possibly smaller than 1 kilometer across. This size range is perfectly reasonable for interstellar debris. Planetary formation processes inevitably produce vast quantities of leftover material in these size ranges, and some fraction will inevitably be ejected from their home systems through gravitational interactions with planets or stellar companions. The forward scattering brightness pattern that has sparked speculation about artificial illumination finds a much simpler explanation in dust physics. When small particles scatter sunlight, the efficiency depends strongly on the scattering angle, the angle between the incoming sunlight and the direction toward the observer. Forward scattering, where light approaches from behind the particles, can be dramatically more efficient than backward scattering for certain particle size distributions. This effect explains why 3I Atlas appears brightest in the sunward direction without requiring any exotic energy sources. The dust grains in its coma are simply scattering sunlight more efficiently when viewed from certain angles, creating an appearance that might look unusual to observers unfamiliar with the subtleties of optical scattering theory. The orbital dynamics also follow natural patterns. The hyperbolic trajectory with an eccentricity around 6.1 indicates an object moving at typical interstellar velocities. The velocity at infinity of 57 to 58 kilometers per second matches exactly what we would expect for debris that originated in the galactic thick disk and encountered our solar system's gravitational well. These speeds are not exotic or artificially contrived. They represent the natural consequence of stellar motions within our galaxy. Stars orbit the galactic center at different velocities depending on their distance and orbital characteristics. When material is ejected from one stellar system and subsequently encounters another, the relative velocities typically fall in the range we observe for 3I Atlas. The near-ecliptic alignment, while visually striking, becomes much less mysterious when viewed through the lens of observational selection effects. Ground-based sky surveys concentrate their efforts near the ecliptic plane for practical reasons. That is where most solar system objects reside and where the observing geometry is most favorable. We are inherently more likely to discover interstellar objects that pass through these well-monitored regions. Additionally, the ecliptic plane is not arbitrary. It represents the gravitational midplane of our solar system, where the combined mass of the Sun and planets creates focusing effects that can preferentially deflect approaching objects toward this plane. The apparent targeting of the ecliptic might actually reflect natural gravitational dynamics rather than intentional navigation. Even the timing of solar conjunction finds a straightforward explanation in orbital mechanics. Any object with a perihelion distance around 1 to 2 astronomical units will inevitably pass through conjunction as viewed from Earth. This is not a designed feature intended to avoid observation. It is simply the predictable consequence of following a hyperbolic orbit with that particular closest approach distance. The sequence of planetary encounters, while superficially resembling a planned tour, results from the same orbital geometry that creates the conjunction timing. The retrograde trajectory skimming the ecliptic plane naturally brings 3I Atlas within several astronomical units of multiple planets. But the missed distances are far too large for any meaningful gravitational interactions. These are not targeted flybys. They are simply the inevitable result of threading a hyperbolic path through a system where most massive objects concentrate near a single plane. Compositional analysis, while still preliminary, shows no obvious departures from expected comet chemistry. The difficulty in detecting specific gas species reflects the observational challenges of studying faint emission lines at large distances, not necessarily unusual chemical composition. Experience with 2I Borisov reminds us that many spectroscopic signatures only become apparent as objects approach perihelion, and heating effects boost gas production to more easily detectable levels. The morphological details revealed by Hubble imaging, the slightly asymmetric dust distribution, the offset between peak brightness and the nuclear center, find ready explanations in the complex physics of cometary outgassing. Real comet nuclei are not perfect spheres with uniform composition. They are rubble piles of ice and rock with irregular surfaces, varying volatile concentrations, and complex internal structures that create localized jets and asymmetric activity patterns. Seasonal effects also play a role. As a comet rotates, different regions of its surface experience varying levels of solar illumination, leading to temporal changes in activity patterns and morphology. Without knowing 3I Atlas's rotation period and axis orientation, we cannot predict exactly how its appearance should evolve, but asymmetric and time-variable behavior is the norm rather than the exception for active comets. The statistical argument provides perhaps the strongest natural explanation for 3I Atlas's apparent unusualities. As our detection capabilities improve and we begin observing larger numbers of interstellar objects, we should expect to find some that display characteristics that appear special or unusual simply due to random variation. The Vera C. Rubin Observatory will potentially discover dozens of interstellar visitors in the coming decade, and basic statistics guarantee that some will have orbital geometries, brightness patterns, or other properties that seem improbable by chance alone. This does not mean unusual objects are necessarily mundane. It means we need to be careful about inferring intention from apparent improbability. In a large enough sample, even genuinely rare events will occur frequently enough to generate false patterns and misleading impressions of design. The accumulating evidence supports a straightforward interpretation. 3I Atlas is an interstellar comet, behaving largely as natural physics predicts. Its unusual characteristics reflect the inevitable variations that occur when studying objects from environments we do not fully understand. Viewed through the limitations of our current observational capabilities, the Comet Playbook, refined through centuries of studying objects in our own solar system, appears to work just as well for visitors from other stars. Part 8. When natural doesn't fit, the gaps and tensions. The most unsettling mysteries are not those where everything appears wrong. They are the ones where almost everything appears right, except for those persistent details that do not quite align. 3. I-Atlas presents us with precisely this type of puzzle, an object that meets most criteria for natural behavior while consistently producing small discrepancies that build up into something more difficult to disregard. Consider the issue of gas detection. At this stage in Tui Borisov's approach to the Sun, spectroscopic observations were starting to show clear signs of water vapor, carbon monoxide, and other expected volatile compounds. These detections were not simple. They needed careful calibration and sophisticated analysis techniques, but they provided the chemical fingerprints that definitively identified Borisov as a natural comet. For 3I Atlas, similar spectroscopic searches have yielded frustratingly ambiguous results. Early efforts to detect water vapor, carbon dioxide, carbon monoxide, and cyanide have only produced upper limits, constraints on how much of these gases could be present without being detected, rather than positive identifications of their presence. This does not prove the gases are not there, but it does suggest they are either present at unexpectedly low levels or the outgassing is somehow different from typical cometary behavior. The absence of clear gas detections becomes more puzzling when compared to the obvious dust activity. Hubble images show substantial coma development and dust production rates that require significant volatile sublimation to lift particles off the nuclear surface. Where is all that gas coming from if we cannot detect the expected molecular signatures? One possibility is that 3I Atlas is dominated by more exotic volatiles that do not produce easily detectable spectroscopic lines. Carbon monoxide, for instance, produces weaker emission features than water vapor and might dominate the gas production without being as readily observable. Alternatively, the object might contain significant amounts of very fine dust that scatters light efficiently while requiring less gas production to become airborne. But these explanations start to feel contrived when stacked against the mounting list of other subtle anomalies. The brightness asymmetry provides another example. While forward scattering can indeed explain enhanced sunward brightness, the degree and persistence of this asymmetry in 3I Atlas pushes against the boundaries of what standard dust models predict for natural particles. Computer simulations of comet dust dynamics typically produce more symmetric coma profiles than what we observe, particularly at the distances where 3I Atlas was first imaged. The sunward concentration appears stronger and more localized than models suggest should occur for randomly distributed particles being pushed by radiation pressure and solar wind effects. Size estimation discrepancies add another layer of complexity. The dramatic revision from early estimates of 10 to 20 kilometers down to just a few kilometers reflects more than simple observational uncertainty. It suggests either the initial assumptions about surface reflectivity were badly wrong, or the relationship between nucleus size and coma brightness is more complicated than standard models assume. A smaller nucleus producing the observed level of activity implies either unusually high volatile content, the object is more icy than typical comets, or more efficient outgassing mechanisms. Both possibilities are plausible, but would make 3I Atlas statistically unusual compared to the population of comets we have studied in our own solar system. The ecliptic alignment issue refuses to go away, despite reasonable explanations involving selection effects and gravitational focusing. While these processes can preferentially direct objects toward the ecliptic plane, quantifying exactly how much bias they introduce requires sophisticated modeling of detection probabilities and interstellar object approach geometries. The existing literature provides rough estimates, but the error bars are large enough that genuinely unusual alignments could still hide within the uncertainties. More troubling is the lack of comprehensive statistical analysis of the complete trajectory geometry. Yes, the ecliptic alignment might be explained by selection effects. Yes, the planetary encounter sequence might result from natural orbital mechanics. But what is the probability of both occurring simultaneously, along with the fortuitous solar conjunction timing and the other subtle anomalies we have catalogued? Proper statistical analysis would require careful modeling of observational biases, multiple testing corrections for the number of different anomalies being evaluated, and realistic prior probability estimates for various natural and artificial scenarios. Such analysis is computationally intensive and methodologically challenging, which might explain why definitive calculations have not appeared in the peer-reviewed literature. The solar conjunction timing deserves particular scrutiny precisely because it is so easily dismissed as natural. While conjunction is indeed common for objects with perihelia around 1 to 2 astronomical units, the timing is remarkably convenient for avoiding detailed observation during peak activity. A truly random arrival time would be just as likely to provide optimal viewing geometry during perihelion passage. The cumulative effect of these gaps and tensions creates what philosophers of science call the problem of auxiliary hypotheses. Each individual anomaly can be explained by adding specific assumptions: unusual dust properties here, atypical volatile composition there, observational selection effects everywhere. But as the number of required auxiliary hypotheses grows, the overall explanation becomes increasingly complex and post hoc. This does not prove the natural explanation is wrong, but it does highlight how our confidence in that explanation depends on a growing collection of assumptions that have not been independently verified. The scientific method functions most effectively when theoretical frameworks produce distinct, verifiable forecasts that can either be substantiated or disproven via observation. With 3 Atlas, the difficulty arises because the majority of suggested natural causes are adaptable enough to align with nearly any finding retroactively. Measurements of its rotation period serve as a perfect illustration of this issue. A clear majority of active comets exhibit noticeable periodic fluctuations in their brightness and form as various areas of their surface rotate into and out of the Sun's light. The lack of any apparent rotational markers for 3 Atlas could suggest an exceedingly long period of rotation, an almost perfectly spherical form, a viewing angle aimed directly at its pole, or a consistent surface makeup. While each of these explanations is individually believable, the absence of any separate constraints prevents me from differentiating between them or evaluating their comparative likelihoods. The way the object's appearance has changed over time is another domain where naturalistic models find it hard to make exact predictions. Cometary activity generally intensifies as an object nears the Sun, adhering to well-understood connections between its distance from the Sun and the rates of sublimation. However, the specific details hinge on the composition of the nucleus, its thermal characteristics, and structural features that are still mostly a mystery for interstellar bodies. This ambiguity makes it challenging to tell the difference between a natural progression that just happens to seem peculiar and genuinely aberrant behavior that conventional physics cannot explain. The problem is worsened by the lack of a significant observational baseline for interstellar comets. I do not yet have a clear picture of what is considered normal for this category of object. What is perhaps most troubling is the possibility of confirmation bias influencing my analysis. Having been predisposed by the anomalies of Oumuamua and the continuing discussion about potential artificial origins, researchers may subconsciously be more inclined to spot and highlight unusual traits while minimizing more conventional explanations. This prejudice can work in either direction, pushing interpretations both toward and away from the exotic. The media focus on 3 Atlas generates further pressure to make conclusive declarations about its nature, even when the scientific investigation is still genuinely inconclusive. Public statements and talks at conferences often highlight the most confidently held interpretations, which could obscure the significant uncertainties that continue to surround crucial observations. I am ultimately left with an object that persistently creates minor inconsistencies between what is observed and what is expected. These are individually inconclusive, but when taken together, suggest that my understanding is still lacking. The central question that 3 Atlas presents to my scientific comprehension is whether these knowledge gaps indicate some form of exotic physics or are merely a consequence of studying unfamiliar objects with less than perfect instruments. What would it signify for a path to be chosen? I can picture myself as a cosmic air traffic controller, observing objects traversing three-dimensional space at immense speeds over distances that are beyond human grasp. What would it even imply for one of those paths to be deliberately selected, rather than being the unavoidable outcome of gravitational laws and arbitrary starting conditions? This inquiry gets to the very core of what I am truly asking when I contemplate whether the trajectory of 3 Atlas displays evidence of purpose. On the most fundamental level, a chosen path would necessitate some kind of active steering, an ability to execute course adjustments that diverge from a path governed solely by gravity. In my own solar system, spacecraft exhibit this kind of capability by firing rockets, which alter their velocity in specific directions at precise moments. These actions leave behind detectable traces in the form of abrupt changes in acceleration that cannot be attributed to gravitational forces alone. Oumuamua offered a perfect demonstration of how faint such traces can be. Its non-gravitational acceleration was a mere 17 meters per second in total, just enough to alter the object's speed by the equivalent of a slow jog over its entire transit through the inner solar system. Nevertheless, this minuscule deviation was detectable because astronomers were able to monitor the object's location with remarkable accuracy over a period of several months. For 3 Atlas, identifying similar signs of acceleration would demand equally meticulous astrometric surveillance. The object's position has to be measured over and over for long durations, with uncertainties slight enough to pick up velocity shifts of meters per second against a backdrop of movement at tens of kilometers per second. It is analogous to attempting to discern whether a person crossing a football field has subtly altered their gait by studying pictures taken from an aircraft. As of now, observations do not show any sign of such trajectory alterations. 3I Atlas seems to be tracing a purely gravitational hyperbola, with its projected future locations aligning with observations within the margins of measurement error. However, these margins are still broad enough that minor course adjustments might be concealed within the observational static. A more advanced method of navigation might entail ballistic targeting, where a trajectory is calculated to meet certain objectives without needing adjustments mid-journey. This method would be significantly harder to spot, as the object would trace a natural gravitational course that just so happens to create ideal viewing angles or a favorable sequence of encounters. This kind of targeting would demand exceptional computational accuracy and sophisticated foresight. The path would have to be determined not only to arrive at my solar system, but to do so with the precise velocity and orientation needed to fulfill whatever goals the guidance system had in mind. The room for error would be incredibly small. Minor inaccuracies in the initial conditions would escalate over interstellar distances into huge positional discrepancies. Still, if such accuracy were possible, the resulting trajectory could be nearly impossible to distinguish from a natural one. The only indications would be statistical, the unlikelihood of random events producing such an apparently deliberate geometry. This leads me directly into the field of probability theory and the difficulty of separating design from mere chance. What particular goals could warrant such a complex navigational plan? The most evident possibility is reconnaissance. An advanced civilization might wish to examine habitable planets, technological indicators, or the general features of other star systems without disclosing its presence. Traveling through the inner solar system would offer chances to study Earth, Mars, Venus, and possibly spot artificial constructions or electromagnetic signals that point to a technological society. Yet the geometry of the encounters of 3I Atlas appears ill-suited for in-depth reconnaissance. The nearest it gets to Earth is at 1.88 astronomical units, roughly 270 million kilometers, which is much too far for high-definition imaging of surface details or man-made structures. Even my most sophisticated space telescopes find it difficult to discern planetary features at such distances. More unconventional goals could include deploying instruments, such as leaving behind small monitoring probes during flybys of planets, which could stay in the system for long-term observation. These probes would have to be incredibly tiny to go unnoticed, and their release would probably generate observable signs like changes in trajectory or trails of debris. Another speculative option is a communication relay. An interstellar body could function as a data courier, gathering information as it passes through the solar system and then sending it to receivers in its home system or elsewhere. This would necessitate advanced communication technology and power sources that could potentially be detected by their electromagnetic signals or heat signatures. The timing of the solar conjunction introduces another layer to scenarios based on intent. If 3I Atlas was engineered to evade close examination during its most active period, positioning itself behind the Sun during its perihelion passage would be a smart move. On the other hand, the conjunction might be the perfect time for actions that require the least observation from Earth, such as deploying instruments, making course corrections, or communicating with other assets in the system. However, these scenarios compel me to make many assumptions about the abilities and motives of hypothetical alien civilizations. I am essentially trying to deduce intent from observed actions, a notoriously flawed method even when analyzing human behavior, let alone the creations of entirely unknown minds working with incomprehensible limitations. The task gets even more intricate when I consider the concept of distributed reconnaissance. Instead of dispatching a single, highly advanced probe, an advanced civilization might send out numerous simpler objects engineered to resemble natural debris while equipped with basic sensor packages. Such a tactic would be much more challenging to detect and could enable thorough monitoring of many star systems at once. Current SETI protocols are mainly centered on radio and optical signals, aiming to find intentional communications or the electromagnetic traces of advanced technology. However, passive reconnaissance objects might not emit any detectable signals at all, looking just like natural debris except for slight trajectory deviations or statistical trends that become visible only when analyzing a large number of objects together. This poses deep questions about what constitutes evidence and the standards of proof I should use for claims of artificial origin. How unlikely must a trajectory be before I start to seriously entertain non-natural explanations? How many seemingly odd characteristics must build up before chance becomes a less convincing explanation than design? The philosophical ramifications go beyond the particular case of 3I Atlas. If advanced civilizations are studying me using disguised probes, my ability to detect such surveillance might rely as much on my conceptual models and analytical techniques as on my technological prowess. I could be encircled by artificial objects that I consistently mistake for natural ones because my ideas about what artificial objects ought to look like are fundamentally flawed. Conversely, my pattern-detecting mind might be producing false alarms, seeing natural events as artificial because I am predisposed to search for signs of intelligence in ambiguous information. The annals of science are filled with instances of phenomena that were initially mysterious, but were eventually explained by conventional means as observation tools improved and theoretical knowledge grew. The matter of intent ultimately forces me to face the boundaries of scientific methodology when confronted with potentially intelligent phenomena. Science is excellent at testing hypotheses against observations, but intelligence is specifically engineered to thwart such analysis by imitating natural processes and evading detection. I may require entirely new methods to differentiate between sophisticated disguise and authentic natural behavior. For the time being, 3I Atlas proceeds on its meticulously orchestrated path through my solar system, tracing a course that could represent either the beautiful certainty of celestial mechanics or the deliberate purpose of minds I cannot even start to fathom. The difference might be less important than my readiness to stay open to both possibilities while upholding the strict standards of evidence that separate science from mere speculation. Envision a galactic gambling hall in which the dice possess billions of sides and the roulette wheel turns through dimensions I can hardly conceive. Each path through space is a single outcome from a nearly limitless array of possibilities. And yet, my brain, which evolved to identify patterns on the African savanna, is determined to perceive deliberate design in what could be just the unavoidable consequence of rolling cosmic dice enough times. This is the core problem in determining whether the trajectory of 3E Atlas is a true anomaly or simply a statistical certainty. When I am dealing with the astronomical scales of space, time, and probability, my gut feelings about what is improbable completely fail me. Let me first consider the fundamental geometry. The ecliptic plane, that unseen disk where my planet orbits, makes up a minuscule portion of all conceivable approach angles for an interstellar object. I can imagine a sphere enclosing my solar system. The ecliptic plane slices through this sphere like an incredibly thin cut through an orange. The likelihood that a randomly aimed trajectory would align within 5 degrees of this plane seems almost non-existent. However, this calculation overlooks critical observational biases that tilt my sample precisely toward such trajectories. Ground-based sky surveys focus their work near the ecliptic for entirely practical reasons. This is where the majority of asteroids and comets are located, where the atmosphere causes the least interference, and where viewing conditions are the most advantageous. I might find 50 objects near the ecliptic for every one I find at high inclinations, just because I am not searching as diligently in other directions. The scenario gets even more intricate when I factor in the effects of gravitational focusing. My solar system is not merely empty space with a star and planets randomly distributed within it. It is a gravitational framework that actively shapes the paths of objects approaching it. Computer models indicate that the combined gravitational pull of the Sun and planets can divert interstellar objects preferentially toward the ecliptic plane, especially if they approach at the relatively slow speeds characteristic of thick disk star populations. To quantify these effects, I need sophisticated modeling that takes into account the distribution of stellar velocities in my galactic vicinity, the gravitational layout of the solar system, and the observational powers and search methods of current sky surveys. These calculations are computationally demanding and heavily reliant on assumptions about parameters that are not known with precision. The handful of published estimates indicate that ecliptic alignments could be several times more probable than simplistic geometric reasoning would suggest, but the margins of error are wide enough that truly rare events could still be concealed within them. I am essentially attempting to differentiate between the improbable and the very improbable using statistical methods that were not created for such extreme situations. The sequence of planetary encounters introduces another level of seeming improbability. What are the chances that a random path would result in close flybys of Mars, Venus, Earth, and Jupiter in a tidy chronological order? Once more, a basic calculation points to astronomical odds against such an event. But close approaches is a subjective term that requires precise definition. The actual missed distances of 0.19 astronomical units for Mars, 0.6565 for Venus, 1.8 for Earth, and 0.36 for Jupiter are substantial by the standards of spacecraft missions. These are not exact flybys intended to harness gravitational energy or meet specific targeting goals. They are merely the unavoidable outcome of a retrograde hyperbolic path weaving through a system where most of the massive bodies are concentrated near a single plane. The key realization is that any trajectory that grazes the ecliptic plane is bound to encounter several planets at different distances. The particular order and timing are contingent on the exact orbital geometry, but some kind of multi-planet encounter sequence is almost a certainty rather than a rarity. I am not figuring out the odds of hitting specific targets, but rather the likelihood that targets happen to be located along a predetermined route. The timing of the solar conjunction offers another instance of apparent fine-tuning that falls apart upon closer examination. The fact that 3I Atlas vanishes behind the Sun during its closest approach seems suspiciously opportune for an object attempting to evade detailed scrutiny. However, any object with a perihelion distance of about 1 to 2 astronomical units will unavoidably undergo a conjunction as seen from Earth. It is a geometric requirement, not an engineered characteristic. The timing is not even especially unusual. Objects with similar perihelion distances include many asteroids and comets that regularly experience conjunctions during their closest solar flybys. If I were to survey all such objects over time, I would discover that a conjunction during perihelion passage is the standard rather than the exception. Yet my brain resists these statistical arguments because they clash with deeply rooted intuitions about purpose and design. When I observe a sequence of events that seems to have a purpose, I instinctively conclude that a purpose exists. This cognitive bias was beneficial for my ancestors when interpreting animal behavior or social interactions, but it becomes a hindrance when analyzing cosmic events that unfold on scales far beyond human experience. The birthday paradox serves as a helpful parallel for grasping how seemingly improbable occurrences can be statistically certain. In a group of just 23 people, there is a greater than 50% probability that 2 will have the same birthday. This result appears counterintuitive until one understands that they are not calculating the odds of a specific match, but rather the likelihood that any match exists among all potential pairings. In a similar vein, as I enhance my detection abilities and start observing a greater number of interstellar objects, I should anticipate that some will exhibit traits that seem unlikely to occur by chance alone. The Vera Rubin Observatory is set to discover dozens of such objects in the upcoming decade, and basic statistics ensure that several will possess orbital geometries, timing coincidences, or other features that appear deliberately orchestrated. This does not imply that unusual objects are necessarily ordinary. It means I must be exceptionally cautious about deducing design from apparent improbability. The calculation must consider not only the specific sequence of traits I observe, but also the selection biases that draw certain kinds of objects to my attention while completely overlooking others. Publication bias further complicates these statistical difficulties. Research articles and media reports naturally emphasize the most intriguing and peculiar discoveries, leading to a systematic skew in my perception of how frequent various phenomena truly are. I hear about objects with extraordinary trajectories precisely because they are extraordinary, not because they are typical of the larger population. The need for multiple testing corrections is another critical factor often ignored in sensational reports about improbable trajectories. When I scrutinize any complex object for unusual features, I am essentially conducting dozens or even hundreds of different statistical tests on its orbital geometry, brightness fluctuations, spectroscopic signatures, temporal changes, and more. The probability that at least one of these tests will produce a seemingly significant result purely by chance can be quite high, even if no real anomalies are present. A proper statistical analysis would necessitate pre-registering my hypotheses, specifying beforehand exactly which characteristics I deem anomalous and what probability thresholds I will use to separate unusual from normal behavior. Post hoc analysis, where I define what is unusual based on what I have already observed, is susceptible to cherry-picking, which can make even completely random data seem significant. The velocity distribution of interstellar objects offers another check on claims of artificial targeting. 3I Atlas travels at 57 to 58 kilometers per second relative to the local standard of rest, which is precisely the speed I would expect for debris from the galactic thick disk population. Higher speeds might indicate artificial acceleration, whereas lower speeds could suggest objects that were intentionally slowed down for capture. The observed velocity is perfectly ordinary. Even the most advanced targeting system would be up against fundamental limitations set by orbital mechanics and energy needs. To achieve a specific trajectory requires not just precise navigation, but also immense energy to counteract the natural inclination of objects to follow gravitational paths. The more accurately targeted the trajectory, the more energy is needed to keep that precision against perturbations and uncertainties. These energy demands increase dramatically with the level of precision required. Attaining the milliarc-second positional accuracy needed for truly targeted planetary encounters would necessitate propulsion systems far beyond anything in my technological arsenal, and such systems would likely leave detectable traces like exhaust plumes, thermal radiation, or electromagnetic interference. The lack of any such traces does not conclusively dismiss the possibility of artificial guidance. Advanced civilizations might have propulsion technologies that function based on physical principles I do not yet understand. But it does imply that if artificial guidance is present, it operates at such a subtle level that telling it apart from natural gravitational movement demands statistical arguments rather than direct physical proof. Perhaps most crucially, I do not have the baseline data required to determine what constitutes genuinely unusual behavior for interstellar objects. My sample consists of exactly 3 confirmed detections, which is hardly enough to establish normal ranges for orbital characteristics, activity levels, or encounter geometries. What seems anomalous for 3O Atlas might turn out to be completely typical once I have observed dozens or hundreds of similar objects. The growing sample size will eventually give me the statistical strength needed to distinguish between natural variation and truly anomalous behavior. But until that larger dataset is available, claims about the improbability of specific trajectories remain highly speculative, relying on assumptions about selection effects, detection biases, and population characteristics that I cannot yet confirm. In the meantime, 3I Atlas continues its meticulously choreographed journey through my solar system, following a path that could be either a cosmic coincidence or a calculated intention. The distinction might be less significant than my recognition that in a universe vast enough to contain billions of star systems and trillions of potential interstellar travelers, even the most improbable events become inevitable with enough time and opportunity. There is an almost magnetic allure to the idea that I am not alone in the universe, and this allure becomes irresistible when I encounter objects that do not fit neatly into my classifications of normal behavior. Oumuamua unlocked this particular Pandora's box in 2017, and 3 Atlas has ensured it stays defiantly ajar, regardless of how many conventional explanations I try to stack on top of it. The enduring nature of the alien probe hypothesis is not solely due to public fascination with extraterrestrial life, although that is certainly a factor. It mirrors a real tension within the scientific community regarding how to strike a balance between healthy skepticism and an openness to extraordinary possibilities. This tension became clear with Oumuamua and now applies to every interstellar visitor that follows. Harvard's Avi Loeb has emerged as the most notable proponent of keeping artificial explanations under consideration. His contention that Oumuamua could be artificial based on its strange acceleration and the absence of visible outgassing ignited a fierce debate that persists to this day. When 3I Atlas showed up with its own set of subtle peculiarities, Loeb and his colleagues quickly applied their analysis to this new arrival. Their method is interesting from a methodological standpoint. Instead of making a definitive claim of artificial origin, they advocate for keeping multiple hypotheses active until conclusive evidence appears. They highlight the ecliptic alignment, planetary encounter sequence, and brightness characteristics of 3 Atlas as features that warrant close examination rather than prompt dismissal. The objective is not to prove an alien visit, but to avoid the premature closing of scientific investigation. This stance has elicited strong criticism from other astronomers who contend that extraordinary claims demand extraordinary evidence and that the current observations of 3 Atlas are well within the spectrum of natural comet behavior. The Hubble Space Telescope analysis, which revealed clear outgassing activity and dust production, has been especially persuasive in shifting scientific opinion toward conventional interpretations. Nevertheless, the debate uncovers deeper philosophical divides about the essence of scientific conservatism. Critics maintain that considering alien probe hypotheses without solid evidence erodes scientific credibility and encourages public conspiracy theories. Supporters argue that being overly conservative risks overlooking genuinely revolutionary discoveries, and that the potential consequences of contact with extraterrestrial intelligence warrant a more aggressive investigation of anomalous objects. The media dynamics that surround these discussions add their own set of complications. News organizations are naturally drawn to the "could it be aliens" perspective because it drives clicks and audience engagement. Scientific articles that describe normal comet behavior seldom make the news, whereas speculative blog posts about artificial objects can become viral in a matter of hours. This imbalance in media coverage can create a misleading impression of the scientific consensus. Academic journals are subject to similar pressures. Papers that propose exotic explanations for astronomical phenomena tend to attract more citations and media attention than those that confirm conventional interpretations. Although peer review offers some level of quality control, the publication system still favors novelty and controversy over the careful validation of mundane explanations. Professional astronomers have to navigate these pressures while upholding scientific integrity. Many admit in private that the current observations of 3 Atlas could support multiple interpretations, but they are hesitant to express this uncertainty in public for fear of fostering premature conclusions or conspiracy theories. This often leads to an artificially polarized public discourse that fails to capture the true subtleties of scientific opinion. The Galileo Project, initiated partly in reaction to the Oumuamua controversy, is an effort to tackle these issues through systematic search methods specifically created to find technological artifacts in near-Earth space. Instead of arguing over the interpretation of ambiguous objects after they have been found, the project intends to deploy instruments optimized for telling natural phenomena apart from artificial ones. This approach recognizes that my current astronomical infrastructure, which is primarily designed for studying natural phenomena, may not be ideal for spotting subtle technological signs. Artificial objects might emit infrared signals that differ from those of natural bodies, have structural features that are visible only at high resolution, or show trajectory changes too minor to be detected with standard astrometric methods. The concept of astroarchaeology expands this idea to include systematic searches for technological artifacts throughout the solar system. Just as terrestrial archaeology examines ancient human civilizations through their material artifacts, astroarchaeology would seek evidence of past visits by studying objects in unusual orbits with anomalous compositions or with suspicious geometries. This framework changes the question from "Is 3I Atlas artificial?" to "How would I systematically differentiate between natural and artificial objects among the wider population of interstellar visitors?" The distinction is important because individual objects will always be open to multiple interpretations, but statistics at the population level might show patterns that point conclusively to either natural or artificial origins. The difficulty is in creating testable predictions that can distinguish between these scenarios. Natural interstellar objects should follow statistical distributions for size, composition, activity level, and trajectory that are consistent with the physics of planetary system formation and stellar dynamics. Artificial objects might exhibit different patterns, such as size distributions that cluster around certain values, surprisingly uniform compositions, or trajectory geometries optimized for specific observational purposes. However, these population-level indicators will only become clear as my sample size increases from the current 3 confirmed interstellar objects to dozens or hundreds. The Vera Rubin Observatory is poised to dramatically speed up this process, potentially offering the statistical power needed to choose between competing hypotheses about the nature and origin of interstellar visitors. Individual case studies like 3 Atlas are still valuable, even if they cannot definitively settle the artificial versus natural debate. Each object provides an opportunity to develop analysis techniques, improve observational strategies, and fine-tune my ability to extract information from limited data. These skills will be essential as the detection rate rises, and I am compelled to make swift evaluations of potentially significant discoveries. The ethical aspects of this research also merit consideration. If advanced civilizations are studying me, my reaction to that discovery could have profound consequences for the future of humanity. The premature release of ambiguous evidence might cause panic or false hope, while excessive secrecy could erode public trust in scientific institutions. The SETI community has established protocols for managing the potential detection of extraterrestrial intelligence, but these are mainly focused on radio and optical signals, not physical artifacts. The discovery of confirmed technological objects in my solar system would necessitate new frameworks for verification, communication, and response that are not currently in place. Public education is crucial in this context. The general populace needs to grasp both the genuine scientific questions posed by objects like 3 Atlas and the strict standards of evidence needed before arriving at extraordinary conclusions. Science communication that either dismisses interesting possibilities or exaggerates preliminary findings can harm public trust and scientific credibility. The persistence of the alien probe hypothesis ultimately reflects humanity's profound need to comprehend my place in the universe. Am I alone, or am I part of a larger community of intelligent species? Do I inhabit a cosmos where intelligence is so uncommon that I might never encounter it, or one where advanced civilizations regularly explore other star systems? These questions go beyond the specific case of 3 Atlas or any single object. They touch upon fundamental issues regarding the nature of intelligence, the probability of technological civilization, and the chance that my seeming isolation is an illusion upheld by species far more advanced than my own. Whether 3 Atlas is a piece of natural debris from another star system or something more remarkable, it acts as a mirror, reflecting my hopes, fears, and assumptions about intelligence in the universe. The trajectory may or may not be chosen, but my reaction to that possibility says something deep about the kind of species I am becoming as I take my first hesitant steps toward understanding my place in the galactic community. As 3 Atlas continues its path toward perihelion and beyond, the alien probe hypothesis will probably endure, not because the evidence requires it, but because the question it raises touches on something fundamental to human curiosity and my relationship with the cosmos that envelops me. Nothing fuels speculation more than a misunderstood trajectory, and few things are more frequently misunderstood than the 3-dimensional geometry of orbital motion. When news outlets initially reported that 3I Atlas would get close to Earth, the headlines created images of a cosmic visitor heading straight for my planet. The truth is both more ordinary and more captivating. This interstellar traveler will weave through the inner regions of my solar system like a needle passing through cloth, getting nowhere near my world while offering a masterclass in celestial mechanics. Let me outline the actual route. On October 3, 2025, 3I Atlas will pass by Mars at a distance of 0.19 astronomical units, which is about 19 million miles. To give this some context, that is approximately 50 times the distance from Earth to the Moon, and almost 20 times closer than Mars ever gets to Earth during its nearest approaches. It is not exactly a collision path, but it is close enough to give a wave if anyone were observing from Martian orbit. The journey continues as 3I Atlas swings around the Sun at perihelion on October 29th to 30th at a distance of about 1.36 to 1.44 astronomical units, just inside the average orbital distance of Mars. This closest approach to my star marks the gravitational high point of the object's visit to the solar system, where it will undergo maximum heating and potentially its greatest activity as subsurface ices turn to gas under the intense solar radiation. On November 3rd, there is the Venus encounter at 0.6565 astronomical units, about 60 million miles from the cloud-covered planet. Once again, this is a relatively close flyby by solar system standards, but far too distant for any significant gravitational interaction or detailed observation of one body by the other. Then comes the encounter that garners the most media attention. Earth's closest approach on December 19th at 1.8 astronomical units. This distance, roughly 270 million kilometers, puts 3 Atlas about twice as far from Earth as Mars is during its closest approaches to my planet. To casual observers reading headlines, approaching Earth might sound alarming, but in astronomical terms, it is a remote flyby that presents absolutely no danger. Finally, the grand tour wraps up with a Jupiter encounter on March 16, 2026, at 0.36 astronomical units, about 34 million miles from the giant planet. This is the closest approach to any planet during the entire solar system transit, yet it is still over 80 times the distance from Earth to the Moon. NASA and the European Space Agency have consistently stated that 3I Atlas presents no threat to Earth at all. The closest approach distance of 1.8 astronomical units offers a massive margin of safety. Even if my orbital calculations were incorrect by millions of miles, there would still be no chance of a collision. However, the persistent media focus on Earth approach distances shows how easily astronomical geometry can be misconstrued by an audience not used to thinking in 3 dimensions across immense scales. The trajectory seems meticulously planned only when seen through the lens of human spatial intuition. I observe a sequence of planetary encounters and envision deliberate targeting, much like a tourist planning visits to several cities on a European trip. But orbital mechanics follows different rules than highway travel or airline schedules. 3I Atlas traces a single, continuous hyperbolic path that was set by its velocity and direction upon entering the solar system's gravitational field. The series of planetary encounters is a result of the simple fact that most planets orbit fairly close to the ecliptic plane, and any trajectory that skims that plane will inevitably pass near multiple worlds. The specific distances and timings are determined by precisely when and where the planets happen to be during the object's transit, not by any navigation system trying to optimize viewing angles. This distinction is vital when assessing claims of purposeful reconnaissance or surveillance. A true probe designed to study my solar system would likely aim for much closer flybys of planets of interest, especially Earth. The actual encounter distances are too great for detailed surface observations or for detecting technological signatures that might suggest intelligent life. Even my most sophisticated space telescopes have difficulty resolving planetary surface features at the distances involved in the encounters of 3 Atlas. The Hubble Space Telescope can just make out the largest features on Mars when that planet is at its closest to Earth, which is about 100 times closer than 3I Atlas will pass. Detecting signs of civilization or even life would require a proximity measured in thousands of miles, not millions. The apparent tour of the inner solar system seems even less remarkable when I consider that 3I Atlas will actually be in a poor position to observe most of these worlds during its closest approaches. The geometry of its retrograde orbit means the object will be viewing the dark sides of planets during many encounters or approaching from angles that offer limited visibility of the surface. More importantly, if 3I Atlas were designed for reconnaissance, why would it restrict itself to passive observation from such vast distances? An advanced civilization capable of interstellar travel would likely possess technologies that could achieve much closer approaches, deploy smaller observation satellites, or establish longer-term monitoring capabilities within the solar system. The most suspicious aspect of the trajectory might actually be its lack of optimization for any clear reconnaissance goals. It is almost as if someone took a genuine interstellar comet trajectory and then complained that it was not following the path a well-designed spy probe would take. The timing of the solar conjunction adds another dimension to the trajectory analysis. As 3I Atlas nears its closest approach to the Sun, it will be positioned almost directly behind my star as seen from Earth, making detailed observations extremely difficult during what should be its most active and interesting period. Some have interpreted this timing as a sign of intentional concealment, an effort to evade scrutiny during its peak activity. But astronomical geometry does not cater to my observational desires. Any object with a perihelion distance of about 1 to 2 astronomical units will inevitably go through a conjunction as viewed from Earth. The timing is not a choice, it is an unavoidable result of orbital mechanics. Hundreds of asteroids and comets regularly pass through similar conjunctions without anyone suggesting they are trying to hide from human observation. The conjunction actually represents a missed opportunity if 3I Atlas were designed for reconnaissance. The period around perihelion, when the object is most active and potentially most observable, coincides with the worst possible geometry for Earth-based telescopes. A competent surveillance mission would design its trajectory to maximize observability during peak activity, not minimize it. Professional observatories are adjusting their strategies to overcome the limitations of the conjunction. Space-based telescopes like Hubble can observe closer to the Sun than ground-based instruments, although even they have restrictions on how close to my star they can safely aim. Solar observatories designed to study the Sun itself might be able to track 3I Atlas during the conjunction, though separating the object from the overwhelming brightness of my star would be incredibly challenging. The post-conjunction observations planned for early December 2025 will be critical for understanding how the object has been affected by its close solar encounter. Many comets exhibit dramatic changes in activity level, morphology, and even structural integrity after passing perihelion. Some break apart under thermal stress, while others develop enhanced outgassing that makes spectroscopic analysis much more fruitful. If 3I Atlas were artificial, these post-perihelion observations might reveal traits that set it apart from natural comets. Artificial objects should be more resilient to thermal damage and might show activity patterns that are not consistent with sublimating ice. Natural comets often become more active after perihelion as subsurface layers are revealed, and volatiles that were previously shielded by overlying material start to outgas. The trajectory ultimately narrates a tale of gravitational inevitability rather than deliberate navigation. 3I Atlas entered my solar system with a specific velocity and direction that dictated its entire subsequent course. The planetary encounters, the timing of the conjunction, and the Earth approach distance are all outcomes of that initial trajectory, altered only by the predictable gravitational pulls of the Sun and planets. Whether that initial trajectory was itself chosen is still an open question, but the passage through the solar system appears to be simply the natural consequence of adhering to gravitational physics from point A to point B across interplanetary distances. Not a grand tour, not a reconnaissance mission, but merely a visitor passing through my cosmic vicinity on its way to somewhere else entirely. What if 3 Atlas is not primarily concerned with studying my solar system, but rather with studying me? This thought experiment takes me into the realm of pure speculation, but it is speculation with a point, to explore how my reaction to anomalous objects might itself be the phenomenon under observation. If an advanced civilization wished to comprehend how emerging technological species respond to potential contact scenarios, they might devise tests that reveal as much about the observers as the observed. The idea is similar to psychological experiments, where the stated goal conceals the true objective. Researchers might say they are testing memory or decision-making, but they are actually gauging social conformity or ethical reasoning. Likewise, an interstellar object that seems to be passing through my system for natural reasons might in fact be engineered to elicit specific reactions that show my scientific maturity, coordination abilities, and readiness for broader galactic interaction. I can consider what 3i Atlas has already achieved in terms of evaluating human systems. Within hours of its discovery, observatories on 6 continents were synchronizing observations through the Minor Planet Center. Professional and amateur astronomers worked together to monitor its movement and brightness. Space agencies released measured public statements, striking a balance between scientific enthusiasm and appropriate caution. Social media erupted with speculation, from insightful analysis to wild conspiracy theories. This global response pattern would offer valuable intelligence about my species' current capabilities and social structures. How rapidly can I organize international scientific cooperation? How well can I distinguish between evidence-based analysis and baseless speculation? How do my media systems manage potentially extraordinary discoveries? These questions might be far more compelling to an advanced civilization than anything they could learn from remote observations of my planets. The timing of the trajectory seems almost perfectly designed to test these systems. The discovery months before perihelion gave enough lead time for extensive observation campaigns, but not so much that public interest would fade. The solar conjunction introduces a natural interruption in observations that tests my patience and my capacity to sustain scientific programs through gaps in data collection. The reappearance after the conjunction presents an opportunity to see how well my predictions aligned with reality. Even more fascinatingly, the object's characteristics appear to be calibrated to produce exactly the kind of debate I am currently having. If it were too obviously artificial, I might panic or abandon space exploration altogether. If it were too obviously natural, I might overlook it without learning anything about my own analytical skills. Instead, 3 Atlas presents me with a puzzle that is genuinely ambiguous, natural enough to avert panic, yet unusual enough to capture attention. The ecliptic alignment is a perfect illustration. It is strange enough to ignite speculation about artificial guidance, but not so unprecedented that it could not be the result of natural selection effects and gravitational focusing. This ambiguity compels me to face the limitations of my statistical analysis, my grasp of observational biases, and my ability to tell coincidence from design. The sequence of planetary encounters provides another test of my interpretive frameworks. Do I perceive a random trajectory that happens to pass near multiple worlds, or a meticulously planned reconnaissance mission? My answer says something fundamental about my inclination to attribute intent to ambiguous phenomena, a cognitive characteristic that might be vital for understanding how I would react to more definite signs of extraterrestrial intelligence. The patterns of media response would be particularly enlightening for external observers. Within days of the discovery announcement, I produced thousands of articles, blog posts, social media debates, and video analyses that covered every conceivable interpretation, from a mundane comet to an alien mothership. This flood of commentary would offer a thorough sample of human reasoning processes, cultural biases, and communication strategies. When confronted with potentially extraordinary phenomena, scientific institutions displayed their own traits through their reactions. NASA and ESA released careful, measured statements that highlighted safety and scientific opportunity while steering clear of speculation about exotic origins. Professional astronomers generally lean toward natural explanations while admitting to lingering uncertainties. The peer review process slowly proceeded through its deliberate method of hypothesis testing and evidence evaluation. These institutional responses would tell external observers important things about my decision-making processes, risk management approaches, and cultural values. How do I balance scientific prudence against public curiosity? How effectively can my institutions control the flow of information during potentially revolutionary discoveries? How do I manage disagreements among experts when the stakes are high and the evidence is ambiguous? The timing of the conjunction could be a particularly clever test component. By vanishing behind the sun during its most active phase, 3I Atlas sets up a natural experiment in delayed gratification and scientific patience. Do I keep up rigorous observation programs even when immediate results are not forthcoming? How well do I predict what I will find when observations recommence? Can I avoid filling the gaps in observation with unfounded speculation? More subtly, the timing of the conjunction tests my technological abilities and international cooperation. Space-based telescopes can observe closer to the sun than ground-based instruments, but coordinating between different observatory systems demands sophisticated communication and data-sharing protocols. Successfully tracking an object through a conjunction requires precisely the kind of technological and institutional skills that would be necessary for broader space exploration and eventual interstellar communication. The confusion over size estimation, from initial reports of a massive 20-kilometer object down to the current constraints of just a few kilometers, would reveal important information about my measurement abilities and error correction methods. How quickly can I identify and fix systematic errors in my analysis? How well do I convey uncertainty to both scientific and public audiences? Do I learn from my mistakes, or do I make similar errors with future discoveries? Even my speculation about artificial origins acts as a form of unintentional self-disclosure. The fact that I seriously contemplate whether interstellar objects might be probes shows both my awareness that I am not necessarily alone in the universe and my assumption that other intelligences would find me interesting enough to study. These attitudes would tell external observers significant things about my level of cosmic awareness and my readiness for contact scenarios. The international coordination aspects of my response would be particularly telling. Despite political tensions and competing national interests, the astronomical community has maintained remarkable cooperation in tracking and studying 3I Atlas. This suggests that my species might be capable of unified responses to cosmic phenomena, even when I have trouble with coordination on purely terrestrial matters. My technological capabilities would also be fully demonstrated. The rapid trajectory calculations, the attempts at spectroscopic analysis, and the sophisticated imaging with Hubble show that I have reached a significant level of technical skill in astronomical observation and analysis. But the limitations of my capabilities, the ambiguous gas detections, uncertain size estimates, and incomplete characterization would also be clear to any observers with superior technology. Perhaps most importantly, my handling of uncertainty itself serves as a key measure of intellectual maturity. Science progresses through careful hypothesis testing and the gradual accumulation of evidence, but public discourse often demands immediate, definitive answers. How well I navigate this tension, maintaining appropriate scientific skepticism while staying open to extraordinary possibilities, could be a crucial indicator of my readiness for cosmic citizenship. If this speculative framework holds any truth, then 3I Atlas is less a test of my ability to detect alien technology and more a test of my capacity to think clearly about ambiguous phenomena under intense scrutiny. The object might be entirely natural, but my response to it reveals authentic characteristics of my civilization that no amount of passive observation could disclose. Whether designed as a test or not, 3I Atlas certainly acts as one, challenging my scientific methods, institutional coordination, media systems, and public reasoning skills in ways that expose fundamental features of human civilization at its current stage of development. In that respect, every interstellar visitor serves as a mirror, reflecting my own cosmic coming-of-age back to me across the vast scales of space and time. The test goes on as 3 Atlas approaches perihelion and beyond. How I handle the remaining unknowns may be more important than what I ultimately find out about the object itself. Science is, at its core, a dialogue between what I believe I know and what the universe actually shows me when I examine it closely enough. For 3i Atlas, that dialogue has been illuminating, frustrating, and at times contradictory, a perfect illustration of how the most intriguing discoveries arise from the gaps between certainty and ignorance. Let me begin with what I can state with assurance. The astrometric data, which are precise measurements of the object's position over time, offer irrefutable proof of its interstellar origin and hyperbolic trajectory. Numerous observatories around the world have monitored 3i Atlas for several months, creating an observational arc that firmly establishes its orbital characteristics with great precision. The eccentricity of approximately 6.1, the inclination of 175 degrees, and the sequence of planetary encounters are as well defined as orbital mechanics permits. The observations from the Hubble Space Telescope are another cornerstone of reliable data. These images distinctly reveal a developed coma, evidence of dust emission toward the Sun, and a faint anti-solar tail, the classic signs of an active comet. Surface brightness modeling limits the nucleus size to a radius of less than 2.8 kilometers and possibly much smaller. The dust production rates of 10 to 120 kilograms per second are within reasonable ranges for cometary activity at several astronomical units from the Sun. Photometric measurements from various facilities consistently show a gradual increase in brightness as the object nears perihelion, following patterns broadly similar to other comets at comparable distances. The color measurements, though still preliminary, suggest properties not drastically different from typical cometary dust, although there are some potential variations that need further observation to confirm. However, these small areas of solid knowledge are encircled by vast expanses of uncertainty that highlight just how much I still do not comprehend about 3i Atlas and interstellar objects in general. The spectroscopic data remains tantalizingly incomplete. Despite dedicated observing campaigns at multiple facilities, efforts to identify specific gas species, water vapor, carbon monoxide, carbon dioxide, cyanide, have only produced upper limits instead of clear detections. This does not necessarily point to unusual chemistry. Faint emission lines are notoriously hard to detect against the background sky, especially for distant objects with moderate activity levels. The experience with 2i Borisov offers both hope and caution in this regard. That object's most unique spectroscopic signatures only became clear as it neared perihelion, and the heating effects increased gas production to more easily detectable levels. 3i Atlas might yet show its chemical composition as solar heating intensifies, but I will not know for sure until the observations are complete and analyzed. Detailed morphological analysis is still constrained by the fundamental difficulties of separating nucleus properties from coma contamination. While Hubble's sharp vision can distinguish these components better than ground-based telescopes, the modeling still relies on assumptions about dust grain properties, size distributions, and scattering efficiencies that introduce systematic uncertainties into all the derived parameters. The rotational state of 3i Atlas is almost entirely unknown. Most active comets exhibit clear periodic changes in brightness and morphology as different parts of their surfaces rotate into and out of the sunlight. The lack of obvious rotational signatures could mean anything from a very long rotation period to a nearly spherical shape to a viewing angle that minimizes rotational effects. Without this information, I cannot predict how the object's appearance might evolve as it approaches the Sun and potentially develops more complex activity patterns. The solar conjunction presents both a logistical challenge and a scientific opportunity. As 3i Atlas moves behind the Sun from Earth's viewpoint, most ground-based observations become impossible due to the overwhelming glare of my star. But this also coincides with the period of maximum solar heating and potentially maximum activity, when any unusual characteristics might become most prominent. Space-based telescopes like Hubble can observe somewhat closer to the Sun than ground-based facilities, but even they have strict limits on how close to my star they can safely aim. Solar observatories designed specifically for studying the Sun might be able to track 3 Atlas during the conjunction, but separating a faint comet from the intense solar background would be extremely difficult. The post-conjunction observations planned for early December 2025 will be essential for resolving many of the current uncertainties. Objects often look quite different after passing perihelion, as thermal processing exposes new surface materials and potentially changes their internal structure. Increased outgassing might finally provide the spectroscopic signatures needed to determine its composition. Changes in morphology could reveal structural characteristics that were not visible during the inbound phase. But even these future observations will be limited by fundamental constraints in my current capabilities. Ground-based telescopes have to deal with atmospheric effects, weather, and limited resolution. Space-based facilities provide sharper images but have restricted observing time and wavelength coverage. No single instrument can supply all the information required to fully characterize an object as complex and distant as 3 Atlas. The ongoing scientific debate about interpretation reflects these observational limitations as much as it does genuine disagreement about physical processes. When key measurements have large error margins or are completely unavailable, multiple explanations can fit the existing data equally well. This ambiguity allows both conventional comet models and more exotic hypotheses to coexist until further observations decisively favor one over the other. Institutional communications have generally leaned toward the most conservative interpretations that are consistent with the available data. Statements from NASA and ESA emphasize the evidence for cometary activity while also acknowledging the remaining uncertainties about composition and structure. This strategy balances scientific credibility with public interest, but it can also inadvertently hide the significant gaps in my understanding. Professional astronomers are faced with similar tensions between admitting uncertainty and providing clear public communication. Qualified statements about what the data might suggest or could indicate accurately reflect the tentative nature of current conclusions, but they can be frustrating for media outlets and public audiences who want definitive answers to straightforward questions. The peer review process continues to work through these interpretive challenges at its typically deliberate speed. Initial discovery papers and early characterization studies have been released in preprint form, but the most definitive analyses are waiting for additional observations and the thorough examination of expert review. This methodical approach serves science well in the long run, but it means that public understanding often depends on preliminary results that may be significantly revised as the analysis progresses. Competing research groups sometimes arrive at different conclusions based on the same observational data, which reflects honest disagreements about modeling assumptions, statistical analysis methods, or the relative importance assigned to different types of evidence. These debates unfold through conference presentations, preprint servers, and eventually peer-reviewed publications, but the timeline for resolution can extend over months or years. The broader context of interstellar object research adds another layer of complexity to the interpretation of 3I Atlas specifically. With only 3 confirmed detections, Oumuamua, 2I, Borisov, and now 3I Atlas, I lack the statistical baseline needed to differentiate between normal variation and genuinely anomalous behavior. What appears unusual for 3 Atlas might turn out to be completely typical once I have observed dozens of similar objects. The Vera Rubin Observatory is set to transform this situation dramatically. With its 8.4-meter primary mirror and 3.2 gigapixel camera, Rubin will scan the entire visible sky every few nights, starting in the mid-2020s. Conservative projections suggest it could find 6 to 50 interstellar objects per year, depending on their size distribution and the effectiveness of follow-up observations. This influx of new discoveries will provide the statistical power needed to address many of the current questions about interstellar objects. Are ecliptic alignments genuinely rare, or do they stem from predictable selection effects? Do unusual brightness patterns indicate exotic physics or natural variations in dust properties? How common are objects with the specific combination of characteristics seen in 3 Atlas? But the Rubin era will also bring new challenges. The rapid discovery rate will tax my ability to conduct detailed follow-up observations of every interesting object. Automated classification systems will become crucial for managing the data stream, but these systems must be trained on the limited sample of objects I have studied so far. Early decisions about which discoveries merit intensive study could skew my understanding of the broader population. International coordination will become even more vital as discovery rates climb. The current system of manual follow-up observations and careful individual analysis will not be scalable to dozens of new objects per year. I will need more efficient protocols for sharing observing time, coordinating spectroscopic campaigns, and distributing results quickly enough to be useful for time-sensitive observations. The experience with 3 Atlas underscores both the strengths and weaknesses of my current approach to studying unusual astronomical phenomena. I have shown a remarkable ability to coordinate rapid, multi-facility observations and produce sophisticated analyses under intense public scrutiny. But I have also exposed significant gaps in my capabilities and understanding that will need to be addressed as such discoveries become more frequent. Perhaps most importantly, the observations of 3 Atlas have provided crucial practice in managing uncertainty and communicating scientific nuance during potentially revolutionary discoveries. The skills I have developed in distinguishing between genuine anomalies and observational artifacts, between reasonable speculation and unfounded claims, will be essential as I encounter objects that may be even more challenging to interpret. The current limits of my knowledge about 3 Atlas reflect the inherent challenges of studying small, distant, fast-moving objects with finite observational resources. But they also reveal the remarkable progress I have made in developing the theoretical frameworks, instrumental capabilities, and analytical techniques needed to extract meaningful science from limited data. As 3 Atlas approaches perihelion and eventually recedes back into the cosmic darkness from which it emerged, the gaps in my current understanding will gradually be filled by new observations and refined analysis. But each answer will likely lead to new questions, and each resolved uncertainty will reveal previously unsuspected complexities in the physics of interstellar objects. The conversation between what I think I know and what the universe actually shows me continues, and 3 Atlas has proven to be a particularly articulate contributor to that ongoing dialogue between human curiosity and cosmic mystery. I now come back to that spinning vinyl record, my solar system revolving in its ancient track, and the cosmic stylus that grazed its surface with such strange precision. 3 Atlas has performed its tune, a composition of ice and dust, orbital mechanics, and human fascination. Now it readies to lift away and vanish back into the quiet between the stars. Yet the question that led me into this puzzle persists. Was that music deliberately composed, or did I simply decide to perceive patterns in cosmic static? The argument against intentional design is built on a foundation of sound physics and statistical logic. 3 Atlas exhibits the hyperbolic kinematics I would anticipate from natural interstellar material moving at speeds common to my galactic neighborhood's stellar population. Its alignment with the ecliptic, though visually striking, can be accounted for by observational selection biases and the gravitational lensing properties of my solar system. The series of planetary encounters is a result of basic geometry rather than directed navigation, with missed distances far too great for any meaningful reconnaissance or gravity assist maneuvers. Most compellingly, observations from the Hubble Space Telescope show clear signs of cometary activity. The sunward emission of dust and a faint antisolar tail, which are characteristic of ice sublimating under solar heat, just as natural physics would predict. The rates of dust production, the constraints on its nucleus size, and its morphological features all fit within the ranges I have seen for active comets throughout my own solar system. No anomalous acceleration signatures have been found, no mysterious energy sources, and no structured emissions inconsistent with the passive solar heating of volatile substances. The apparent anomalies that first fueled speculation have plausible explanations rooted in the complex physics of small body behavior and the limitations of my observational tools. Forward scattered dust produces brightness patterns that can seem odd until one understands the principles of optical scattering theory. The confusion over its size arose from the difficulty of separating the light of the nucleus from the contamination of the coma. Spectroscopic ambiguities are a reflection of the inherent challenges in detecting faint emission lines against the background noise of the sky at distances of multiple astronomical units. And yet, something about 3R Atlas continues to trouble the edges of scientific certainty. The accumulation of small oddities, the precise ecliptic alignment, the opportune timing of the conjunction, the persistent asymmetries in brightness, the lack of clear gas detections, forms a pattern that defies easy classification. Each individual trait has a potential natural cause, but the combination feels statistically improbable in ways that are hard to quantify with precision. This uncertainty provides room for ongoing curiosity about more exotic possibilities. If 3 Atlas were artificial, it would be a perfect example of the sophisticated mimicry I might expect from a civilization advanced enough to master interstellar travel. If it were too obviously technological, it might provoke panic or hostile reactions. If it were too obviously natural, it would teach me nothing about my detection skills and analytical techniques. Instead, it occupies a perfect middle ground, natural enough to prevent alarm, yet unusual enough to demand attention and reveal my true scientific capabilities. The reconnaissance hypothesis has clear flaws. The planetary encounter distances are much too large for detailed surface observations or for detecting technological signatures. The timing of the conjunction actually hinders rather than helps observational opportunities during its most active phases. If surveillance was the aim, the trajectory seems almost intentionally suboptimal for collecting useful information about Earth or other potentially interesting worlds. But perhaps surveillance is not the objective. Perhaps the real goal is something more subtle, a test of my detection abilities, my analytical methods, and my institutional reactions to potentially extraordinary discoveries. Within this framework, 3I Atlas is a brilliant success, regardless of its physical nature. It has exposed my current observational boundaries, my coordination systems, my media dynamics, and my cultural assumptions about intelligence in the universe. The timing of its arrival feels meaningful in ways that go beyond orbital mechanics. I exist in a unique period of human history when my astronomical capabilities are sophisticated enough to find and study interstellar visitors, but not yet advanced enough to definitively determine their nature and origin. I can measure trajectories with remarkable precision but have difficulty with compositional analysis. I can organize global observation campaigns but am still susceptible to observational selection biases and interpretive prejudices. If an advanced civilization wanted to gauge my readiness for broader cosmic engagement, they might create tests that probe exactly these abilities and limitations. 3I Atlas has certainly achieved that, sparking worldwide scientific collaboration, intense public debate, and a detailed review of my methods for distinguishing natural phenomena from potential technological artifacts. The question of by whom takes me into even more speculative domains. If 3 Atlas was chosen, its creators would surely possess technologies and abilities far beyond my current comprehension. Interstellar navigation with enough precision to achieve specific trajectories in the solar system would demand not just advanced propulsion systems, but also computational power capable of modeling gravitational interactions across light-years of space and decades of time. Such civilizations might have motives entirely beyond my grasp. Perhaps they conduct systematic surveys of stellar systems, documenting the evolution of potentially intelligent species. Maybe they are looking for something specific, signs of particular technologies, evidence of certain physical processes, or indications that younger civilizations have reached particular milestones in their cosmic journey. The why question might be even more alien to human thought. My speculation naturally centers on purposes I can conceive of: reconnaissance, communication, resource evaluation. But truly advanced intelligences might have goals as incomprehensible to me as quantum mechanics would be to a medieval scholar. I might be posing the wrong questions entirely, searching for familiar motives in phenomena that operate on a completely different logic. Still, there is something wonderfully recursive in the idea that 3I Atlas is testing my capacity to recognize and analyze potential artificial phenomena. If the trajectory was chosen, perhaps the choice was made not just to study my solar system, but to study me, to see how a young technological species reacts when confronted with ambiguous evidence of intelligence beyond its own. In this view, my entire scientific and cultural response to 3 Atlas becomes part of the phenomenon under observation. My meticulous measurements, my heated discussions, my media coverage, my institutional coordination, all of it adds to a comprehensive picture of human civilization at its current stage of cosmic awareness. The elegance of this interpretation is that it holds true regardless of the actual nature of 3 Atlas. Even if the object turns out to be entirely natural, my response to it reveals authentic traits of my species that no amount of passive observation could disclose. I am, in essence, testing myself by proxy, using an ambiguous stimulus to probe my own capabilities and assumptions. As 3I Atlas continues its journey toward the outer solar system and eventually back into interstellar space, it takes with it, consciously or not, a complete record of humanity's first systematic effort to characterize a potentially artificial interstellar visitor. Whether that record is of interest to anyone but myself remains gloriously unknown. The stylus has played its tune and is starting to lift from the vinyl surface. Soon it will vanish back into the cosmic void, leaving behind only measurements, memories, and the persistent question of whether I heard music or just the scrape of a needle in a groove. In the end, perhaps the choice was mine all along, the choice to look up, to measure, to wonder, and to stay open to possibilities that challenge my understanding of my place in the universe. If the trajectory of 3I Atlas was chosen, then somewhere among the stars, intelligences I cannot fathom are observing how well I listened to their cosmic composition. If it was not chosen, then I have composed my own music from the raw materials of orbital mechanics and human curiosity. And that composition reveals something equally profound about the kind of species I am becoming as I take my first tentative steps toward cosmic citizenship. The mystery persists, not because I lack the means to solve it, but because the most significant mysteries are those that teach me something new about myself in the process of seeking. 3I Atlas has given me that gift, regardless of whether its trajectory was determined by alien intelligence or cosmic chance. In the end, perhaps that is the choice that truly matters.